All right. Welcome back, everyone. This morning we are happy to have Yishai Mansour from Tel Aviv University. He's made fundamental contributions to bandits and reinforcement learning and online learning. And I can't wait to see what he's got in store for us today. Take it away.
Okay, thank you very much. Okay, so I guess the title of the talk is in line with the title of this workshop. I'm going to talk about linear quadratic control and online learning. I'll try to keep it at a high level and basically try to give the ideas of two joint papers with Alon Cohen, Avinatan Hasidim, Tomer Koren, Nevanan Lazik, and Kunal Tiwari. Okay, so what is online learning? I think online learning is one of the successes in machine learning, and especially on the theory side. We have both the bandit and the full information setting, and the original motivation is sort of coming in order to sort of, from the health domain, to select between different procedures to give. But over the years, it had many applications, especially in internet advertising and in internet sales. So this is sort of one well-established domain, which I think we understand fairly well today, both from the theory and the practice side. Reinforcement learning, I guess, is the topic of this workshop. It has many applications and many more applications that we will really like it to have. Sort of the success stories are coming mainly from games, but we would like to see reinforcement learning applied in other places, like autonomous driving, robotics, etc. So the intersection of reinforcement learning and online learning is sort of not empty. There are sort of very obvious candidates to put there. Online MDPs is a one setting in which the costs are changing arbitrarily, similarly to adversarial online learning, but you are in an MDP setting. A different setting is UCRL, which is like an upper confidence bound for reinforcement learning, much in the style of stochastic bandits. So I guess the third thing that I would like to add today is the linear dynamics, or the LQQR. I would like to combine both ideas from reinforcement learning and online learning and apply them to the linear dynamic setting. Okay. So I'm going to go slowly, I warned you. What is control in general? So in general, we have an agent. It does an action, so that we're going to sort of mark the actions by UT. It goes to the environment, and then we observe two things. We observe the next state and the cost. This is a general reinforcement learning picture, but when we are speaking about the linear dynamics, really what we mean is that the action space is a k-dimensional vectors. The linear dynamics really implies that there are two matrices, A and B, such that A times X plus B times U plus some Gaussian noise is the next state. So this is the linear dynamic part. And we have a cost. The cost is quadratic, so we have two positive definite matrices, Q and R, and the cost is X transpose QX plus U transpose RU. Just to make life easier, if you want to think about the cost now, think of it as some kind of norm of X squared plus norm of U squared. Okay? So at a high level, coming from reinforcement learning, when I see this picture, there is two obvious things that was done here, right? A very explicit dynamic and cost was put on the table. This is the simplifying part. On the other hand, it's sort of a continuous domain, both continuous action and continuous state space. Okay, so linear control has many applications. Probably some of you know it better than me. In Google, sort of the original motivation that we looked at the problem was climate control in data centers in order to save both energy and to get a better control schemes, but it sort of has been applied in robotic, finance, and in many other places. Okay, so let me sort of, just to make sure that everyone on the same page, although Ben did a nice introduction of the model yesterday, let me sort of re-say a few things that I think most of you are familiar with. Okay, so what is a policy? So a policy would be a mapping from states to action. So in this case, it's going to be a mapping from a d-dimensional vector space to a k-dimensional vector space. We'll be interested both in the finite horizon and infinite horizon. So in the finite horizon, we are looking at the sum of the cost for t time steps. And in the infinite horizon, we'll be looking at the average cost, assuming this limit exists. And it normally would exist under very mild condition. When we're looking at the infinite horizon, this is probably the more intuitive way of thinking about those systems. It's like a steady state of the system. Then I guess it shouldn't be surprised that since the dynamics are linear and the cost is quadratic, then the optimal policy is also linear. So what does it mean? It means that there exists a matrix K such that the optimal policy is K times X. Okay, and there is, some notion that we need to get into, but not too much. Okay, so those systems might be stable or unstable. So what is a stable system? Stable system, if you take the matrix K, right, this is sort of your policy, and you look at how A plus BK is changing. You look at the eigenvalues of this matrix, you like all the eigenvalues to be less than 1. The way to think about it is that sort of A plus BK is the way that you're going to modify the previous state to the next state. If the eigenvalues are less than 1, then things would hopefully converge. If they are more than 1, it's in some sense hopeless because it means that they will diverge. So this is a property of a matrix K, but it's stable. And if it's stable, it also, it's well known. It induces a steady state distribution, a stationary covariance matrix. In a sense, what will happen is that if you look at the covariance matrices that it will generate over time, they will have a limit, and the limit is sort of going to be the covariance matrix K. Okay. A very brief introduction to LQR. So now let's try to look at it from the lens of machine learning. So when I see such a model, like there is two obvious places to think, okay, what would happen if things would behave differently? One is costs, right? Sort of, when I define things, I said, okay, the costs are quadratic and known. What happens if the costs change over time, right? So in many applications, it's natural to assume that the costs change over time, either abruptly or drifting. So what we will be, so one paper that I'm going to describe will be looking at the case when the costs are changing over time in an adversarial way. Adversarial we will still keep the matrices to be positive semi-definite, but they will be coming in arbitrary order. Sort of, we'll have no idea what is the next sort of set of costs that we are going to get. Yes?
Just so I understand the notion of time here, so am I thinking that at
T
least in the
time
finite,
steps.
okay, so time steps, not trajectories. Yeah.
Yeah, time steps.
Yeah.
Yeah.
Because
Okay.
you should
Online
say
learning.
finite
Right.
horizon, you know.
No. Okay. I was able to confuse. Right. So, online. I'm an online learning guy. So when you have uncertainty, think online learning. Yes. Thank you Alex, for the question. Yeah. So in both cases, I'm thinking about a large T-step horizon, large because I want to ignore constant and small size effects. Right. The other interesting case is sort of what happens when you have uncertainty in the dynamics. Sort of unknown dynamics. Basically, you don't know the matrices A and B. And we look at the realizable cases. There is a set of matrices A and B describing the dynamics, and this is a recent work from the last ICML. Okay, and there are also other works in this domain, and when I sort of get to describe it, I'll go into more detail about the previous works. Sort of, but this is sort of the high level of the talk, right? So the main thing that I'm going to look at is regret. So regret would be the difference between how much is my algorithm paying in expectation over a T horizon versus what would an optimal algorithm. And now we'll need sort of to discuss what do I mean here by optimal. So what I would really like to compare myself to is the true optimal. But what we really do is compare ourselves to the best single matrix, which needs to be sort of also strongly stable. I will need to define it later. So the comparison is sort of how well is our algorithm doing, and we are comparing it in some sense to what the infinite horizon would do by selecting a single matrix and running with it. In both cases, sort of our aim is to get a low regret, vanishing over time. And in both cases, where we are showing a square root regret bound, both for the changing cost and for the unknown dynamic case. OK. And I think it's a very interesting question. Why did we discover, we as the machine learning community, discover LQR only in the last 2 years? I have to admit that Csaba was before everyone else. Knowing the future, he started in 2011. But there seems to be a surge of works on LQR in various other aspects of machine learning. Many of them also have to do with learning parameters of the system, stability, and other aspects. And I think it's fair to say that many of the works are sort of borrowing ideas for machine learning and trying to apply them in a sophisticated way on linear dynamic systems. And I think this is sort of for me, one of the challenges of this workshop is to understand the other viewpoint, people coming more from control theory and learning how to do this change. So for the rest of the talk, I'm sort of going to have two parts. One is going to talk about the changing costs, and one is going to talk about the unknown dynamics. So let's start talking about the online linear quadratic control with changing costs.
Yishai?
Yes?
I mean, may I just suggest why? I mean, the first paper, 2017, I know why we wrote it. Which is, I mean, and it was just because at that point we had our big deep RL revolution. I was told that we could solve all robotics problems with deep reinforcement learning, and I wanted to know, can you actually, what happens if you run it on LQR? What's the simplest problem?
I see.
That's why we started looking at it.
I see, because we solved all the other problems.
Every other problem.
Right.
Yeah.
And this is what was left.
I don't know. I think the claims were pretty big, and so we were really curious about like, what happens if you run it on something simple. So,
Okay.
And that required us to actually try to figure out what a baseline was. It was cool that there's lots after that. Where's
And
Chop?
this is Csaba is it.
Chop, why did you guys look at it?
It's just a beautiful problem. It's just
That-
nice.
I think earlier than that there was like a kind of a one-off work by Feature who tried to do a pack analysis of
Yeah.
LQR, and that was like in 96.
Right.
I mean, he did the EQ before Cohen's and
Fichte.
precursors.
Yeah.
Fichte.
When
I
was
don't know where it is.
That was
where
like-
he went to industry and then
Yeah.
disappeared.
That was-
But that was his PhD thesis.
Laughing at us.
Yeah. So it's interesting. It comes in blips.
Yeah, but like,
That was the same time as your policy grading paper. That was the feature.
yeah, but like Emma was doing this stuff for the whole time, like when he was a postdoc.
But that wasn't theory. Right? I mean,
Emma, he
Emma,
was doing like algorithms. with
Algorithmic, yeah.
exactly.
Okay.
He was in that.
Quadropy.
I tried to grab the attention back to me. Sorry. I love hearing you. Okay, just to set up the problem sort of more specifically. Right, so right now, think of a known dynamic. So you really know the matrices, which really, if you think about MDPs, you know the dynamics of the systems, and you have a changing cost. So in some sense, it very much reminds me, it should remind you of the online MDP stuff, like Sham, myself, and Eyal Evendar did it a long time ago. But this is sort of in an LQR setting. So the agent observes the states and selects an action. And again, what is the goal? So the goal is to minimize the regret, the cost that the agent observes, compared to the best single policy. And the policy here is defined by a matrix. So what would be our basic sort of approach? And I think this approach will reappear in the second work. And I think it sort of is shared by many other works as well. So, of course, we have the original setting that we'd like to solve. But rather than solving it, what we usually do is it's much easier to think on a different setting. Rather than thinking of what our action will impact the environment, we would like to think of an idealized setting in which we sort of switch from one steady state to another steady state. Sort of ignore the effects of time, ignore how much it takes to get to a steady state. Just think that sort of, as you are selecting a policy, you switch to a steady state. So now when we are switching from steady states to steady states, you're basically in an online setting because you're selecting an action. An action is called a policy. Here a policy is a matrix, who cares? But when you select it, you get something that I'm calling a steady state. Here it's going to be a covariance matrix. And it defines you a loss, right? So if you think about, if you have the steady state behavior of a policy, it really defines you a steady state loss. And the steady state loss or cost is really what the online learning really is about, right? So now you can solve it as an online learning problem and optimize it. You need to be careful because the online learning is going to suggest something that you need, which is really telling you move from this covariance matrix to this covariance matrix, from this steady state to this steady state. You need to be sure that you can map it again to a policy. So the next step is sort of taking what the online learning is doing, mapping it back to a policy, and then the policy is really what's being run in the original setting. Okay. So this is the picture that I want you to have in mind. And really what my talk is about is not about the specific result, but something that I think is more interesting than the specific results. It's more like an algorithmic methodology sort of on how to think about those problems and sort of an SDP formulation of the idealized setting. Okay, so let's look on this SDP problem. So capital sigma is going to be my covariance matrix. So this is sort of in the steady state. What is the covariance matrix of both states and actions? So, so I can express my expected cost as an inner product between the cost matrices and my covariance matrix. And really what do I want to do? When I take my covariance matrix, it has like 4 parts, depending whether it's covariance of x, u, the action, or x and u. So really what I want is sort of have the stationary condition that given that sigma is a covariance matrix, what I'll get out is consistent with it, right? This is, and the third line, just ignore it. We need it for the, we'll need it sort of in order to really guarantee both the computation and later when we look on the sets, right? But so essentially, right, what is the problem doing? It's looking at the covariance matrices in steady state. It has a feasibility condition, and it's trying to minimize overall. So notice, this is minimizing overall positive semi-definite matrices, sigma. This is why we need the trace condition, so that it wouldn't run away. Okay, and the most important thing is that the true sigma, like the true thing that you would have used if you knew everything, is always feasible here. Okay?
Sorry, why do you need that to
The last one? It's more technical, it's a sort of that. So when I'm solving things, I don't want things to blow up. I'll need to get to it later.
Yeah, if you have a minimum eigenvalue, like are you setting mu as a function of the time?
But I'll get it to it later, but I don't. Let's put it on the side. Okay. Okay. So now, when I'm setting it this way, right? So now I can set it like in an online learning problem and doing an online gradient descent. So essentially, right, my regret is now I'm getting the losses. So the losses is remember now is this matrices composed from QT and RT, right? And we are assuming that they are bounded. So we have our regret, and what we subtract from it is sort of the best sigma that you can find for all the sequence. So this is sort of comparing the best single matrix to what we did in the online setting, right? Yes.
Are you just calling this trace upper bound the strongly stable condition, or?
Strongly stable, and I'll get to define it. Yeah. Okay. Okay. So we need the S are bounded. The S is going to be the feasible SDP solution, and we will need the property that the matrices are changing slowly, right? And this is a property that online gradient descent will have. That essentially, as we are updating things with gradients, our different solutions are not going to change widely. Yes?
The covariance matrix, sigma, is it, are you solving it with QT and RT, or
No,
the SDP solution?
so I'll get to it sort of slightly later, but but I'll be solving it for everything. Right? So it's like in the online learning, sort of. You take all the losses that you saw so far. You don't know the current one, so you're solving for the current one. You found the sigma t now. You're applying it, and then you get a new loss, right? So in the online learning, it's sort of the cycle is that you're selecting an action. In this case, is the sigma t, and what you're getting back is the new loss, which are the new sort of QT and RT. And then for the next step, you're going to use them. At time t plus 1, you use QT and RT and everything that's before of it. Okay. So the next step is sort of, we are solving all now for covariance matrices. We need to be able to map them back into a policy. So again, sort of, this is part of the technicalities that I didn't want to get into it. So essentially, our matrix sort of, it will take the covariance matrix. It will have the part which is sort of the covariance between the action and the state. And you get the part which is the covariance between the states. And this will define the matrix K. So technically, what we also need is sort of to add some Gaussian noise, for our proofs to go through. And the Gaussian noise sort of will be selected from a matrix which is like an uncertainty matrix regarding this sigma that we solved. Okay? So the important thing is when we choose our policy this way, it induces a steady state whose covariance matrix is sigma, right? And if sort of the Gaussian noise in the system is sort of not zero, the feasible solutions are going to be strongly stable, and and the next slide will define the strong stability condition. Okay, so this is, right, we started in the original setting. We set up an SDP program to solve. The SDP program solutions are used in the online linear optimization. We did the gradient descent. You can do other things. And when you take this solution, you can define the policy, and you can run the policy for a single step, right? So what is sort of what you should be aware is that you're solving for the idealized case, but you're running it for a single step every time. And this is why it's also important that the policies do not vary widely. Okay. The strong stability condition, and we'll have another one in the next slide. Okay, so a matrix, it would be, we'll call it to be strongly stable if the following, so what, okay, so stability, remember, is that all the eigenvectors are less than 1. So this would be slightly more than this. So when I'm looking at the matrix A plus BK, I want all the eigenvectors to be less than 1. But what I really want now is also that it will have a decomposition to an L and an H, and you can write as H, L, H to the minus 1, where the eigenvalues of the L's are bounded away from 1, and the K and the H are bounded by some constant kappa. So now you can see when I'm taking this matrix and raising it to the power, right, sort of the dominant thing is going to be the fact that L has an eigenvalue less than 1, because this is going to be raised to the power, and the kappa is going to be some constant which will be multiplied from the both sides. Okay, so this is strong stability. We need something slightly more than strong stability, which we call sequential strong stability, because we are going to modify the matrices as time progresses. It's not the most elegant slide I would hope for, but essentially it's the same idea, right? We would like that the matrices that we generate are strongly stable. We can verify it. And now we need sort of to match the parameters of the different H's that things would work out. Okay? So what it would guarantee us, okay, this is probably, okay. Right, this is sort of what we would like it to guarantee us, right? We would like it that when we are generating a sequence of these matrices, we would like them to be and they are sequentially strongly stable, then, okay, assuming that they have the right steady state and the steady state do not change by much. If you remember when I sort of talked about the SDP, I said that the solution do not change by much. This is why I needed it. Now I can sort of bound the difference between the true thing and the observed thing. And this bound is sort of what I will use in order to analyze my regret. Yes, Chaba.
What's X hat T?
Is the covariance matrix of states in action.
Under what?
Under pi t. Pi t is the policy that you chose at time t.
Okay.
So pi
And
t is defined using kt.
the difference between X hat T and XT is what?
Oh, this is, oh, okay. You're bounding the difference in time t plus 1 compared to the difference in time t.
I'm just wondering what the
This is-
definitions of XT and X hat T, like how do they, like what's the difference between definitions such as?
This is sort of-
like your covariance matrix at time t with your notice.
Right.
Conditioned on the current state.
Condition of the current policy, right? There's no state because you're imagining a steady state. Right? Like, okay, so remember sort of what you are doing here, which sounds sort of strange, is like all the time you are sort of imagining when you are choosing a policy, things will converge immediately to the steady state. Yeah, you will get a loss on the way.
Basically, you want to just say you're close to your asymptotic covariance matrix because you're mixing fluid. Sure, that's what I'm saying.
Okay. And at a very high level, sort of, here's how the, okay, what is the regret composed out of? Right. So the first thing is sort of, it will be composed of the fact that what you think is the steady state and what is truly the steady state in the idealized setting is not identical. And the sequential strong stability needs to take care of it. The second thing is that you're doing an idealized regret. You have a regret. Even if you switch immediately to the steady state distribution, you still have a regret there This would be the second thing. This is the online learning would take care of that. And the strong stability of the optimal policy should take care of the difference between sort of what is the true covariance matrix of the optimal policy versus what you think is the covariance matrix of the optimal policy. So when you plug it in, and I'm not going to do it, those three parts are sort of what composes the regret. Each one would be bounded by square root of t. Okay, so we are almost done with the first part, but okay. Following our work, there was sort of two improvements to our work. The first one by Algorithmic, Bulin, Hazan, Kaka, and Singh. And they were able to extend the work not only to quadratic forms, but to adversarial noise and convex costs. And the second improvement, I think it's still in the working, getting a logarithmic regret. So we show a square root t regret. They are getting a logarithmic regret for Gaussian noise and quadratic costs. Sham is, okay, I didn't see the paper, but I do have an assurance from Elad.
I think you need stronger assumptions for that. I suspect yours can't be improvable unless you have like much stronger assumptions.
Okay. Okay, I completely trust you given that I didn't see the paper. Okay, go.
So these sort of state feedback go around
State feedback. Yeah, state feedback.
With perfect, yeah.
Simplest.
Yeah. Okay, so I guess in the 10 minutes that I have, I want to talk about the other paper. But any questions, right? Okay. Okay, so the second work is sort of, I think it's reusing, oh, sorry. Nothing is simple.
Square root t, what's the dependence on sort of dimension?
It's polynomial, but
It's
they don't.
polynomial.
Yeah, it's polynomial.
And why can't you just use continuous multiplicative weights as opposed to gradient descent?
We use one gradient descent, one follow the leader. You can use whatever you like there, right? It's like you have all the properties that you like in the online learning, right? Because things are changing slowly. You can, right? We do have another sort of, in the paper we have two implementations. Okay. Okay. So now I want to talk about the unknown dynamics part. And let's see how much. And okay. Okay. So what is the problem? Just to make sure that everyone is on the same page and I'm also on the same page. We don't know the matrices, but we do know the costs. I think this is sort of a classical problem of identification. The agent observes the states and selects an action. And again, our goal is to minimize the regret. Again, strong stability will play here a role. And the main result would be sort of a regret which is square root t and a polynomial in the dimension. And the main thing is going to be computationally efficient. And this is sort of comparing it to the previous work. I think the first one was by Abbasi and Chaba in 2011. They show that the regret really scales with square root of t, but they had an exponential dependency on the dimension, and they didn't have.
That
was additive? Okay, sorry.
Still
But it wasn't efficient, right?
No.
Okay.
It's
1 out of 2 is not
exponential.
good. It's fine.
The later was fine, but
Okay. So later Ibrahimi and Al improved the regret bound, but still it wasn't inefficient. Din et al., which I'm going to mention later, showed like a t to the 2/3 explore-exploit algorithm, which was efficient. We show a square root t poly D algorithm. And I should mention that Mania et al., it's not their main result in the paper, but using their results and their lemma, similar results could be derived from their work also. Okay, so the main thing that I wanted is sort of to connect the two works and sort of resell you this basic idea that I worked so hard so far to sell you, and show you that it really can be reapplied again also here. So if we go back to the SDP formulation, this is sort of what we have. This is the main thing. Now the main issue is that if we write this SDP formulation, of course, we are missing something. We don't know the A and we don't know the B. We don't know the dynamics. Okay, so the most obvious thing, and if we're going to do it, we'll plug into A our estimate of A, we plug into B our estimate of B. But this would change sort of what we really need to solve, right? Because now the A hat and B hat are not the true dynamics anymore, right? So we will have, let's say, an approximation error. This is the delta. And we will, and essentially we'll have a matrix V, I'll let you define. But assuming that the trace here is bounded, right? This is the new program that we would like to solve. Notice that we are plugging in our estimated dynamics, but this is sort of like a correction term. And its main goal is sort of to keep the set of solution to include with high probability the right solution, the optimal solution. So this is sort of enlarging the set of solution so that it will include the optimal solution. Okay. So again, sort of what we are going to do here is what many of the other works did, is optimism in face of uncertainty. Either we'll observe a small cost, which is great, or we're guaranteed to do some exploration. Okay. So let me start with sort of two basic ideas and then sort of try to explain our work, and then I probably need to wrap up. Explore, exploit. This was done in Dean et al. 2018. Okay, you basically sort of use during the explore part basically you're sampling some Gaussian distribution. Now you have enough samples, and then you can go and solve for basically a regression. Sort of you're finding A hat and B hat. So at least the first time that we saw that this was proposed to doing this in linear dynamics was in 50 years ago. But I guess this is so obvious, it shouldn't be surprising. So you have the samples. Given the samples, you can solve for the dynamics. Given a model, you solve for the model, and now you executed what you solve. So now when you separate the explore and the exploit, this is where you get the T to the 2/3 trade-offs. Those in online learning, I'm sure, sort of feel comfortable with it. Now, when you're doing optimism in face of uncertainty, this is sort of the work in Abbasi and Chaba. So what you are doing is sort of you are keeping a set of feasible solutions, and which includes the true one. You're solving for the policy that minimizes the cost over all the models in your feasibility set. Now you're executing this, right? So notice that when you are minimizing over this set, you're not really minimizing something real. You're just saying there are many models, and this is the best model. If this is the model, then it's great. You execute this. You get back the feedback. You update now. Given what you observe, you can update the version space. What are the feasible solution? And you reiterate. So essentially, this, at a very high level, guarantees you a square root T regret. And what you are really guaranteeing that sort of every time that you are executing, what you think the solution was, the cost was, is less than what the optimal cost was. Because the optimal model, the true model is always in the set, and you're selecting the best model out of it. Okay? And the problem is that the problem is not convex in the policy parameters. This is why I said their solution was not efficient. So here's the intuition for our algorithm. Right? We're going to run sort of in phases. This is similar to what they did. Right? And when we are running in phases because when we switch from phase to phase, we do incur some cost. Right? So those are the phases. We're not going to have too many phases. Like with high probability, the number of epochs will be bounded by log t. And this should have, and given that we'll have a warm start, that we sort of learn the parameters to some accuracy at the beginning, we can get a total regret, which is square root of t. And how much time do I have? 2 minutes?
5 minutes. There you go.
10?
So much
10?
more.
Anyone?
So much
Anyone? Anyone can give me more?
Before we go to the opposite.
Yeah. Okay. So the basic algorithm, right? We are running at the beginning a warm start. Essentially, we are choosing actions randomly from some Gaussian distribution. And afterwards, we are running in epoch. In every epoch, we are sort of selecting a policy using our semi-definite program. We execute this policy during the epoch. So every epoch has a single policy. And when you switch from one policy to another, this is where you lose the log t because you need things to restabilize. And an epoch ends is when the sort of uncertain, when the determinant of the doubles, sort of when the uncertainty set sort of shrinks, essentially. So this guarantees you that the number of epochs is only logarithmic. And during every epoch, right, we are estimating the parameters from the past, right? So given everything that we observed, we are sort of solving for the dynamics. And given the solution from the dynamics, we are solving our SDP. And this is sort of the main difference, right? By adding this additional thing to the constraint, this is becoming a positive semi-definite program which you can solve. And this additional term is really what guarantees you that the true things would lie inside here. Okay. I know it's very hard to digest, but let's keep it at this level. Okay, I'm starting to wrap up, sort of. One issue that I think it's important to say, but it's sort of technical, is that there is an issue when you think MDPs and you move to LQRs, there is an issue of boundness, which never comes up in MDPs. Because MDPs, the state space is bounded. It's not a real issue. In LQR, you might have a small probability when you're trying to control the system that it will run away. Right? So essentially, you will, you can have a small probability of getting very large value.
Wait, what do you mean, Misha?
Okay. Right.
What do you mean by that K is stable? You mean it's a stabilizing controller?
Yeah, right. Even if you run a stabilized control, you still have maybe an exponentially small probability.
Or not. You can have a very high probability of having a very large value, right? I mean,
Even if you have a very small probability.
Yeah.
Okay, I guess I'm saying it's a non-zero probability that you will get very high values,
Yes.
right? And this might have an unpredictable effect on the expectation. So we were hoping that it will cancel out somehow, but sort of technically we weren't able to show it. But it's something that we should be aware of, right? Even if it's an exponentially small probability, when it blows up, it's exponentially large. And when you multiply those two exponentially, it's not clear that you're going to get something small. Okay? So essentially what our guarantee is a high probability guarantee. Right? We generate sequentially stable policy, and we keep the states bounded with high probability. Right? This is sort of the inside of our proof that I didn't show you, but really what our proof says is with very high probability, all the states are bounded, and therefore, given that all the states are bounded until now, you can continue sort of by induction.
You're saying you can't do this just in expectation?
So in the expectation, we weren't able to show it.
Even with this contraction?
Yeah, because even if you take...
Because you're just working with the matrices and they're
Right.
contracting, why can't you just do...
Because there is a tiny probability that we will diverge.
The states can explode faster than the probability.
Right.
Okay.
Okay. Sometimes it works, sometimes it doesn't, but we won't be able to show either way. Because okay, you have an exponentially small probability that it will grow, but when it grows exponentially large. And now it's two exponents, and suddenly the constants are important.
Stable, so why is it growing at all? You're always in
No, but you have noise. The Gaussian noise is sort of, you're very unlikely in the Gaussian noise, right? And very unlikely, it's like an exponentially small probability. So the high probability result is your intuition, right? I don't expect the low, I expect that the Gaussian noise will behave nicely. We usually it translates to expectations. Somehow we won't able to get
sorry.
it.
Right, I see. This is because you're looking at your somehow actual cost and not the expected
Yes.
conditional cost.
Yes.
If you look at the expected conditional cost, it should be.
No, but even in the expected, you have a tiny probability of having huge cost. Okay. Okay. So. So I think the SDP representation, sort of that I tried to sell you, not sure how many bought it. I think it can have more applications because it talks in a very intuitive way, at least right now for me, sort of how can you model the system? You are modeling it using the steady state, and you can later sort of transform this steady state into a step-by-step. Okay? I guess that sort of the dependency of the bounds on the dimension, although it's polynomial, it's not clear sort of what is the right dependency. I'm rather sure that I think we have like the power of 3, d cubed, but I'm sure this is not sort of the right dependency. And sort of thinking of it at a very high level, I guess we would like to go beyond linear models. I have no idea what we can hope to do realistically, efficiently when we go beyond linear models. And I guess I'm done here. Yes.
One question while Emma sets up.
So I had a question why you need to, in the second part, if you have noise in the system, or even if you don't have noise in the system, the first algorithm you're adding noise anyway. So why do you need to do any phases? Like you can just estimate the system on the fly, and you don't need to do any exploration because there's noise.
Because when we are changing, okay, the way we analyze it is when we are changing policy, we have a loss of something like a logarithmic loss every time we change a policy. And if we do it on the fly.
It doesn't matter. The information you're getting from A and B, like you're always getting information about A and B.
Yeah, but okay. So technically, what really happened when we when we switched is that every time that we switched, we had a loss, and this is why we didn't want to switch many times. I think you had the same issue.
If you measure the pseudo regret, not the actual regret, then you won't suffer the switching cost. And Shem might derive that you can save effect.
But this is for the second part. It's not the estimation. It just seems like in
like information it doesn't really matter that you're not estimating as you go. Like doubling is just fine. Like you're not getting too much information. You're not losing much there.
Sure.
It is more like if you care about the actual regret, actual high probability regret, then you have this mixing cost to pay. And then you don't want to switch to open because
but he's already not switching up. Let me
Okay.
Maybe we're keeping on schedule. We have lots to discuss in the discussion section.
Okay.
Thank you. Up next is Elazar. He's an algorithm maestro. He's been working in reinforcement learning and control for many years. Professor at University of Washington. Recently, his work on Mujoko has really made huge contributions to modern deep learning and reinforcement learning. And I very much look forward to some cool demos, which I'm sure we'll see.
I recently ditched you guys and decided to be a businessman, and it's a good life. No teaching, no grant writing, no meetings. I cannot explain to you how good the life is. Okay, so I'm going to talk about model-based control specifically for, for physical systems. And let me start with some general comments. So when you do machine learning, you have the world, it generates data for you, and then you learn from the data, and the data is the only thing you know. You don't really know much beyond it. When we do control, something else happens. We have, of course, data. We do system ID, we build a model. And then when we do control synthesis or optimization or whatever, we use the model most of the time. Even those of us who run around claiming to be model free, look at what they actually do. They have a model and promise you that one day when the moon is right, we're going to switch to real world, but that never happens. Now, interesting thing what happens when you have a model is you can treat it as if it's the world, send actions, generate data from it. But here the data is essential because that's all you know. Here the data is just made up. What do I mean by that? Well, the data is implicitly contained in your model. In fact, the model contains all the data in the world. Why are you sampling from something when you already know the answer? And it's OK because you can practice for a distant future when RL actually becomes model free, as in you don't actually have a model, and one day switch those. But you're missing out because if you get rid of the middleman here and connect your optimization box directly to the model, you can get a lot of stuff out of the model that's not in the form of data. If you're coming from machine learning, you might ask, how can something not be data? Well, there are lots of things that are not really in the form of data, like equations are not really data. You can ask the model to give you the math that's in it, for example. Can't sample it. In practice, what we do in robotics, there are lots of things you can compute. For example, end-effector Jacobians, these are very useful things that give you the mapping from joint velocities to end-effector velocities and tell you how to go to targets without doing any learning, which is in microseconds. A lot of robots are controlled that way. You can get derivatives of dynamics. You can do inverse dynamics, which I'll talk about. You can look at what is the subspace that are actuated. You can get those analytically, not have to learn them. Distance fields, if you have geometries, those are very useful for planning and putting potential fields and collision avoidance and such. Stability criteria like center of pressure or force closure for locomotion. Lots of things that can just be computed, and it would be silly not to do so. Now you could say, OK, well, if you build a control with respect to a model when you run it on the real world, is it going to work? That's a pretty legitimate question. Well, it does quite often. So let me just go briefly through a few videos to remind you that it does. There are no proofs here. Why are there no proofs here? I mean, there are heroic people who do robust control and try to provide certificates, whatever. All these people come up with assumptions that are not valid in the real world, and therefore, those certificates are not for real. I mean, it's nice to have some theory, but the reality is that when you're controlling a real physical system, there is not a single assumption that you can actually verify. So, oh, yeah, that thing is really true. So it isn't. So we have to look empirically to see, well, does it work? This is the classic work of Peter Beale, flying helicopters with model predictive control. Has a model of the helicopter, flying upside down, doing all kinds of crazy things. Not a perfect model, but it works quite well. There's now a lot of drones that have some kind of model, do MPC through it, and they fly happily around. Here is the work from Evangelos Theodorous group in Georgia Tech, where they put a model of this little car on a GPU that's in the car, and they're doing model predictive control in real time. And it's doing some crazy things like sleeping and whatnot. Works perfectly fine. Fully model-based. Here's something we did. This is interesting. Here, you're learning a model on the fly, and then you're optimizing a trajectory with respect to that model. Then you're playing the trajectory on the system, collecting some more sensitive data, relearning the model. And the model is just a time-varying locally linear model, which is why you can learn it in like 10 or 15 iterations. So this is pretty amazing. So this 24-degree of freedom hand learns to turn this object in a total of 75 repetitions of that behavior, and that's it. Because there's enough data to learn a local model and control around it. This is an example where the nominal model isn't good enough. So we had to create an ensemble of models that are slightly different, only 10 of them. And then we plan a trajectory that's feasible with respect to all 10 of them. And the idea is that if something works for 10 different models in simulation, it probably works for anything in between. And hopefully, your real system is somewhere in between. And this little guy does that. This is particularly nice. So this is planned how to get up from the ground with all kinds of collisions and frictions and such. And it actually does it. And here's, of course, the OpenAI thing that I'm sure you've all seen, which is another example of this domain randomization idea. But in this case, they're actually learning policies and not just trajectories. And so this is actually quite remarkable when it came out. So you give it a desired cube orientation, and it manipulates the cube to put it in that orientation. And so there are multiple approaches here. Model predictive control is just optimizing a trajectory through the model in real time and shifting the horizon. Offline trajectory optimization, I'll talk more about today. You can use this to optimize longer, more complicated trajectories. Policy gradient, you know what it is, a neural network in this case. They could be nominal models, they could be adaptive local models, they could be randomized physics models, all kinds of things you could do. Of course, you could also do model-free RL, but there's some issues. The existing results, especially from Sergey Levin and other people around Berkeley and Google, they're really impressive, but they're impressive because of the computer vision. In other words, if you took away the computer vision, you had full state estimation, nobody would care about those results. They would correspond to solved problem in robotics from 30 years ago. So the fact that these things actually work with vision in the real world without Vicon markers, without anything, that's amazing. But that's because deep learning for vision is amazing. It's not because of the control success, really. They work well in quasi-static tasks where sampling can be safe and automated, so you can actually get it off the ground. You could extend that regime a little bit by having specialized objects, like, for example, this is what my former student, Vikash, has been doing. He's going to be giving a talk tomorrow. But if your hand that is trying to learn how to manipulate an object is dropping the object all the time, you could just mount the object on a motor and make sure it doesn't go anywhere, and you can spin it. And so that greatly simplifies learning, but clearly doesn't scale very well. Now, this is important. There are clearly situations where building a good model is just a nightmare. And in some sense, control is easier than modeling. But that does not automatically mean that RL is a good idea, because those may be situations where sampling is just, you shouldn't even think about it. Like, for example, controlling a bulldozer. How many people would volunteer to sample a bulldozer while sitting in it?
What's the hard modeling part there?
Well, the interactions of the dirt with itself, how it compresses when you roll over it. I mean, you can do something approximate to like 1,000 spheres that are glued, and you get the notion of pushing. But the notion of like what happens when you roll over it and how it compresses look, anything could be modeled given enough effort. That's not the question. The question is, should you put, if your goal is to control and not to model it, should you put that effort first into an accurate model and do model-based control, or should you just go do something else? There are clearly situations where you should go do something else. Another actually very simple situation is this. If you just want rigid grasping, all you have to do is close your fingers. I mean, what is the object going to do? It has to end up somewhere in your hand, right? You don't have to understand every single thing that happens. So there clearly are very simple control strategies with a small number of knobs you can tune. And if you tune those right, it's going to work. But that's not at all reinforcement learning. In fact, that's not learning at all. That's just human creativity and engineering. And I think in the situations that are too hard to model, most of the time it's really human creativity that solves it and not any form of learning. Of course, there are situations where, yes, go ahead, yeah.
So you would say that iterative improvement of a repetitive task is not learning?
Sorry, what?
Iterative improvement of parameters in a repetitive task is not learning?
Sorry, I mean,
I don't know.
Fine.
I'm happy to say that's not learning.
I don't care if it's learning or not. It's a different type of learning, right? It's a very heavily structured control architecture with a small number of gains you're tuning. Sure, yeah. I mean, we can call it learning if you want, but it's completely not obviously what people want to talk about. Now, there are also situations that you could model, like, for example, is Boston Dynamics humanoid, but still people prefer to do manual design and do it very carefully, and they're doing better robotics than anyone else on the planet by laborious manual design, not even by model-based optimization, just by a bunch of really smart people tweaking knobs. But before that, tweaking the knobs, deciding what knobs to create for themselves so they can tweak those. That's the tricky part. That's what we don't know how to automate. Once the knobs are there, anyone can tweak them. But what knobs do we put there? And what's the machine with the knobs on top of it? That's the hard part. So you need models to do that, and you better be able to simulate them. So throughout this talk, I'm using this simulator called Mujoko, which I've been developing for now 11 years. And that's what enabled me to leave academia behind and just sell software licenses. So you can simulate all kinds of systems. There are various robots, there are tendon-driven things. You can play Jenga. It's actually really hard to play Jenga because getting all the contact interactions right is a nightmare. You have all kinds of robots. You can have humanoids sliding on the MathWorks height field. It's very important to have it there. You have like 1,000 spheres. You have clots these days. You can have a humanoid on a hammock. You can tie ropes with the mouse. If you try to do it to reinforcement learning, apparently people are trying and failing for the time being. But I'm sure somebody will release something at some point. The simulator itself is very robust, just the task is hard. You can do spongy things. You can even have like skeletons with like 90 muscles attached to them. So we can simulate lots of things. Just to introduce a bit of notation, Q is position, V is velocity, tau are applied forces. There's some bias terms in inertia metrics. J is a Jacobian of contacts and maybe other constraints. Lambda are constraint forces or contact forces. So forward dynamics, you would think that physics would be a solved problem, but it isn't because of constraints and especially contacts. And what I mean by it's not a solved problem is that there's no formula that tells you what the equations of motion are. To compute the equations of motion, you actually need to solve an optimization problem numerically at every time step in order to know how the universe advances from one time step to the next. And so you might ask, what will happen if the universe fails to solve that problem? Does it like end? Thankfully, it solves it every time, so we don't know how it does it. But when we do it, we have to solve an optimization problem. In Mujoku, that optimization problem happens to be convex after a lot of work that I put into reformulating the physics of contact so it can become convex and yet reasonably realistic. In most alternative simulators like physics, ODE, Bullet, etc., it's actually solving a non-convex problem, which is like a LCP with a non-positive definite matrix. But anyway, so forward dynamics is done through numerical optimization. It's very fast. You can see some numbers here. So for example, a full humanoid flailing around on a 10-core processor, you can collect 300,000 samples per second on a desktop processor. Importantly, this thing also has inverse dynamics. So what inverse dynamics means is given the position, velocity, and acceleration of the system, I can compute the force which generated that acceleration and that position and velocity. So if you want to think about what's that in an MDP, so MDP forward dynamics is given the state and the action, the MDP tells you the probability over next state and it gets sampled from that. The inverse dynamics would be given the current state and the next state that you observed, what would the posterior over actions, and obviously for that you need some kind of prior, and it gets messy very quickly, and it's probably not very useful. But in continuous control, that's actually an extremely useful quantity.
In all your problems, it's properly constrained, meaning that like it's not underdetermined. The inverse dynamics.
The inverse, no, not at all, never. So. I mean, this is actually very simple. So the forward is a solution to optimization problem, which just happens to be convex. So we know the global minimum is given by setting the gradient to 0. Yeah. This simply says the gradient of that is 0, and it's rearranged.
And so I'm just saying we're guaranteed that that thing is strongly convex.
Oh, yeah. Because this is basically, strongly convex. This just says F equals MA penalized with the inertia matrix, which is always symmetric positive definite. And this is adding something that is weakly convex.
But
yeah.
Do you mean that like the inverse dynamics is feasible, like no matter how I set V dot and whatnot?
Exactly. So this is a soft contact model and soft constraint model. For any crazy thing you may choose to do, there exists a finite, possibly very large force, which would have made the system do that in that configuration. When we do optimal control, we're going to say that we don't like very large forces, and all of this will be pruned out automatically, but we can handle it. Now, inverse dynamics, as I mentioned, it's something very useful in control. So again, just forward means mapping from position, velocity, and force to acceleration, and then you do numerical integration. Inverse means mapping from position, velocity, and acceleration to tau. If you have that, you can do really simple things like computed torque control. Namely, you plan some desired trajectory, which is a sequence of positions over time. You compute the velocities and accelerations numerically. Use inverse dynamics to figure out the force which will have given that trajectory, and you play that force in open loop, and you can put some closed loop around it. That probably accounts for more applications of control than everything else combined. And these things can work amazingly well, as you're probably aware. Here's a little industrial robot doing fast and accurate and crazy stuff. And it just works.
Is this data?
No, this is called what is it called? The Adept something or other. It's one of the good industrial robots. Of course, this is very limited. It basically has to be a fully actuated system, but if it is fully actuated, we're done. Kind of. Now, here's a general algorithm based on the notion of the inverse dynamics and the fact we can use it. So we're going to represent the trajectory. So we're going to do trajectory optimization here, no control law for now, just trajectory, as a sequence of poses from time 0 to t minus 1. So this big Q is our decision variable, is the thing we're trying to optimize. Define velocity accelerations with finite differences in time. Run your physics and geometry computations to compute the applied forces and all kinds of other things you may care about. Define some trajectory cost, which depends on all of the above, but it's additive over time, and of course that's key to having efficiency. If there are constraints, under actuation constraints are particularly important in inverse dynamics. Because as we said, you can postulate any trajectory and there is always some force that would have generated it. In some cases, it's obviously a bad idea because you're trying to penetrate the wall is pushing back, you're going to penalize that. But the more subtle and more important thing is that if you have a passive system, like some of the degrees of freedom of this object are not actuated, right? So I should not be putting force directly on the position and orientation of this object. I'm only allowed to do that through contact interactions. So when my inverse dynamics outputs tau, that tau better be 0 in the dimensions where I don't have a motor or a muscle attached to the system. And that's really important. If you don't do that, you just do wishful thinking and you fly to space and you're done. So these are nonlinear equality constraints that are really important. You could also impose inequality constraints by saying that the control shouldn't get too large. I tend to not care too much about that because you can just do that with soft, like half quadratic costs, and as long as you keep it far from the largest controls, you don't really care. If you want to do something really like bang-bang control where you're really going to saturate your motors, fine, but people usually want to operate things in a regime where they're not about to fall apart. And so this is just a straightforward optimization problem. The way I like to solve it is to form an augmented Lagrangian where you end up estimating the Lagrange multipliers online and use the Gauss-Newton method. One thing that's very important here, which kind of relates to the cost being additive over time, is that the Hessians end up being band diagonal. Here, in this case, I actually allow cyclic trajectory. So if you want to compute a movement that repeats itself, I can say that the first state and the last state are the same. I don't know what they are, but they should be the same. So that's actually an interesting example where you cannot apply dynamic programming because there is no time axis. Time has a topology of a circle now. But it's perfectly fine optimization problem, and it's very meaningful from a control perspective. So if you do that and you factorize your Hessian, it ends up being an arrowhead matrix with Cholesky factorization, but it has these big wide regions. And now if you add more time steps, obviously the complexity of this thing grows linearly. So if you look at Riccati equations, basically it's an alternative way to exploit that sparsity. It's just a recursive factorization of a band diagonal Hessian. Whether you do it like that or you form the whole thing and just hit it with Cholesky, it actually makes no difference. So let's see an example of that. So, oh my God, the lights are bad. So here's this little hopper that you can barely see. It's a cyclic trajectory, 200 time steps, 10 milliseconds each, so 2-second movement. I'm constraining it. I have two hard constraints at two poses of this thing, up and down, so it can somehow has to transition between the two. Just a control cost and nothing else. Here's what it does. So the initial trajectory, how it's initialized, is just an interpolation between the two poses. And after it's optimized, it does that and goes through all the contacts. The optimizer considers all the forces explicitly and figures it out. Happens over time. How long did it take? This took 245 iterations in a total of 700 milliseconds. So these are 1,000 decision variables, meaning 200 time steps, 5 positions each. So we optimize 1,000 real values in 0.7 seconds if we do it right. This is something really interesting. So this is somewhere in the middle of the optimization. These are time step over trajectories. The different colors here are the different joints. So this thing has 5 joints. And this is the gradient. So I'm plotting the gradient itself as a trajectory, which, right, so it is. And you can see that it has this very spiky nature over time. Why is it so spiky? Because whenever there's a contact, if you change the configuration a little bit, the forces change a lot, and it's extremely sensitive to that. And then if you're somewhere else, you change things, and not much happens. So you get these very, very badly behaved gradients. If you try to do first-order gradient descent on this, you're going to be stuck instantly, right? Because following the gradient is a bad idea. You end up with trajectories that are clearly going to be suboptimal. But here's the good news. You use Gauss-Newton. So we're not just following the gradient. We're multiplying the gradient by the inverse of a Gauss-Newton Hessian. And when you do that, that nasty spiky thing becomes that perfectly reasonable smooth thing. And now this is a trajectory deformation or search direction that we can go explore. So basically, how does that happen? Well, the Hessian has the right scale and captures the right correlations among the variables. So it cancels this nastiness here and produces something nice. And that's the magic. So without that, like first order gradient set again, like forget it, basically. Now, of course, we can also use the forward dynamics and do model predictive control. Over here, what I did is this took like 200 iterations to converge because we started from scratch. Remember, we started with this thing that just goes up and down like dramatically. In MPC, the way you do it is you already have a trajectory that you optimized. This is your initial state. You start executing it. The world deviates from that. You optimize a new trajectory. But when you optimize the second trajectory, you warm start with the first one. So normally, you have time for only one Gauss-Newton iteration when you do MPC. In fact, if you have time for more, an argument could be made that you should either make the horizon longer or reduce the time step instead of running more. I mean, it's kind of an empirical question. But the point is that warm start is the reason why MPC ever works. Of course, you have to do it fast. So you need efficient physics simulation. You need good optimization algorithms. This iterative LQR is something that I published a while ago. It's basically the Gauss-Newton version of differential dynamic programming from Jacobson many years ago. And it has some clever robustness tricks. And cost functions have to be designed really, really carefully. In this global inverse dynamics thing, the cost function can be something very basic, and it figures it out because it has many iterations. When you're doing MPC and you have only one iteration, you'd better design your cost carefully. So the game you're playing here is you as a human problem designer are heuristically guessing what the value function might look like. And the thing that you're calling a cost is really a bit more like a value in your head. Like as far as the optimizer is concerned, it's a cost. But if you just put what's called a sparse cost, probably not going to happen. But then again, tweaking the weights on a cost function is not that hard. You pick the 5 or 10 terms that you believe are relevant to your problem, and just tweak them and watch it, because the thing is happening in real time, right? You don't have to wait for a month for your neural network to converge. It actually happens in milliseconds. So these things.
Why do you need the ILQR here versus if you have a warm start? It's just the other methods just aren't amenable to warm starting?
Oh no, this is amenable to warm starting. Nobody is using these things for MPC right now. I'm actually about to start doing that. My feeling is that these are more powerful and more robust, but a bit slower. The shooting methods are, when they work, if you read the old books on numerical recipes, what they tell you, shoot first, relax later, right? So this is a relaxation method, the other one is shooting method. If that works, you should use that.
The shooting could be more stable, just like if there's any kind of noise in the system, or it's like multimodal, it seems like you actually want to consider, I mean, maybe if you did ILQG with like multiple linearizations along different
Like an ensemble thing?
Yeah, basically. So
You could do that, but you can also do the other thing in ensemble mode as well. In fact, people here in this department, Zoran Popovic has done, and company did that a while ago with have an ensemble of trajectories and put CMA on top of it, and that actually was really good. The Darwin video is also kind of.
Do you think like the ensemble?
The ensemble definitely gives you robustification at the expense of n times more computation.
But the shooting is very cheap.
No. Shooting and the computational speed, like what you have to do per iteration, is the same for all of these. Like I said, the Hessian is band diagonal, and the derivative and everything is the same computation. The question is how many iterations does each take, and what happens during the line search. Sorry, what?
Because it's in the simulator, it's in the same computation.
Yeah.
Like
Well, it's always going to be. MPC is always going to be a simulator, right?
Some of these things you don't get the derivatives out of it. So then
If you don't have the derivatives, yeah. So if you don't have derivatives, then you have to ask yourself, where do you get the derivatives? Yeah. Then shooting methods have an interesting advantage that you could actually shoot a bunch of trajectories without derivatives, do linear regression, you approximate the derivatives, and do the Riccati equations with those. That can be a good trick. In fact, some people in Europe working in computer graphics have done that, and they've gotten results that are like comparable to ours, in some cases even better. Let me show you some of our old results. So this is a humanoid that's asked to get up. The cost basically says put your torso over the feet, don't move too much, and there's some angular momentum trick. So There's some tricks here, but at the end, it works in real time on a desktop. So we pull it, and it figures out how to save itself and how to get up again. So these are all invented on the fly. This was done like 7, 8 years ago now. You can do guys on unicycles. You can do. This is an interesting example, actually. So here, we're changing the cost in real time, and you can see that. Well, what's going on? Okay, previously he was driving around and trying not to fall. Now we told him that he really shouldn't move, so he started using his arms more to balance. So you can really change the behavior that comes out of it by changing costumes. This is something that Vikash did. The idea is to get an object and put it somewhere, and again, it's MPC. So these methods can work, not always, and they're not that robust, but when they work, it's pretty amazing that they work because there's no learning, right? It just makes it up on the fly, and you're done. Now, of course, there's no reason not to do learning, and recently what we'll do is combine MPC with value functions learning. So let me just talk about this first. So we're going to minimize over a sequence of controls up to some horizon in the future. Normally, we'll just do that. That's how you do MPC. And then what happens on the horizon? Well, nothing, because you don't know what happens afterwards. But what if you had it approximate to the value function? Then you should add that to your MPC cost and optimize that, right? Because MPC just plans, OK, here's my trajectory from here to here. And is it a good thing to be here? Well, I don't know. So I need some function to tell me that. This is the exactly equivalent to the Monte Carlo tree search, for example, that the DeepMind people did in AlphaGo, where they learned some kind of value function. It's not good enough to play by itself, but when you put tree search on top of it, it cleans it up. In control, there's no need for tree search, simply because if you know the initial state, you could allow the thing to search for a tree of trajectories, but what happens is all of them collapse to the same thing, because there's usually one optimal trajectory starting from the state that you're in, and the sensitivities are kind of smooth. Unlike a game scenario where the opponent takes one different move and that sends the game on a completely different path. That doesn't usually happen in continuous systems.
You could imagine some obstacles and you have to go around left and right.
Exactly. So you have to make up an example where that happens. Like if the obstacle is exactly in front of you and left and right is exactly equally good, or if you're standing, you want to start walking, you could start with the left foot and the right foot. Yeah, you could make up examples so that they're rare, and it doesn't matter how you resolve the symmetry.
Someone would say that those are the interesting examples where you have those kind of obstacles.
Oh no, obstacles are interesting, but obstacles are usually not exactly on your path to the target, so it's obvious which side you should go.
Well, but something more complicated than just obstacle navigation.
Well, so I can tell you that people did that, and they showed demos, and in their demos, the so-called tree actually collapsed into a trajectory, so they wasted their time. It may be slightly more robust in some situations, and it goes back to the shooting that you're talking about. If you're going to throw a bunch of things, you might as well make them deviate a little bit and then interpolate. And so then how do we learn this value function? Well, if we have a bunch of quasi-optimal trajectories, then the optimal value function has to be consistent with them through a Bellman backup, right? And so we can use that to do offline learning. This is some math that, I basically told you what matters. Here's some examples. This guy was trained to go and push this cube and has to make it stop. And the ground's slippery, so he's doing these heroic maneuvers to make the cube stop. This is the OpenAI thing that we can now do roughly 100 times faster than they can in simulation because of this trick. The sampling complexity is a bit hard to count because there are complications in both cases, but it's a lot faster than what they were able to do. So this is a good method. Now, we're even doing some exploration in value functions, but I won't talk about that. Now, looking more generally, the pattern here is this. You have a joint optimization between some global parameters and a bunch of trajectories. And you can think of it as a joint optimization problem where you minimize both the trajectories and these global parameters. Now, you can use ADMM or iterative methods and fix one and optimize the other, but it starts out as a joint problem. And there are lots of instances of that that are all interesting. The last I showed you is called POLO, plan online, learn offline. So here the theta mean the value function parameters, and this cost L is just the optimal control cost, plus a consistency cost saying that the value function has to be consistent through the Bellman backups with your trajectories. Another example is guided policy search, which is quite popular. Sergey Levin and company developed that. So in that case, you learn policy parameters. And again, you have a consistency condition, but in that case, consistency is between trajectories you're optimizing and the policy. You could do system ID, where now the meaning of the parameters is some model parameters, not policy parameters. And what's the meaning of the cost? Well, you have some price over the model parameters most likely, and now you have an estimation cost. Right? You want your model to agree with your sensor data for those model parameters. You can also do optimal mechanism design, where again you parameterize the model, and you ask yourself, what robot should I build so it can walk, for instance? So you can do that is you can leave a bunch of real valued parameters undefined and go solve that problem jointly, where now you both generate locomotion behaviors and figure out what the parameters should be at the same time. So it's a very general and very useful thing. It again has this arrowhead structure because now all the trajectories line up here. We're not going to allow limit cycles here because it's more of a control setting. These parameters state that they affect the cost at all times, so they form dense rows of this Hessian. But again, if you add more and more trajectories, the thing grows linearly and factorization is efficient. How am I doing with time? When do you want me to end? 10:35, okay. Now, here is the thing that you could do adopting this sort of deterministic. So you probably noticed that I treat the world as being deterministic, because guess what? That screen has been here throughout my talk. It didn't shake. I don't know if you noticed. So the state transitions of the MDP are actually delta functions. You could, of course, stochastic control is a very exciting thing. There are lots of situations where you can apply it. The physical world is not one of those situations. There's quantum noise, but it's negligible. That's why Newtonian mechanics actually is a pretty good description of the world. So this whole notion that, oh, the world is stochastic, no, it's not. It's deterministic. It only starts shaking when you shake it, either because you don't know what you're doing or because you're shaking it intentionally. Both of these are bad ideas. I'm not sure which one is worse even. Of course, I'm not saying you shouldn't explore. If you really want to explore, fine, go explore, but there's no reason to do so.
Or the wind.
What? Yeah. The wind is not noise. The wind is not noise. You don't understand the wind. That doesn't make it noise. First of all. Second of all, it's not at all stochastic. No. Hold on. So, this old quote from Mike Jordan when I was a student, probability is a model of our ignorance. The wind is not noise. We just don't know what it is. So we call it noise. We capture some statistics that happen to match, but they completely miss the point. It's not noise. In particular, if you look at wind, it doesn't jitter randomly.
If you think this is a well understood thing, right?
Of course, it's a
you're
well understood.
marginalizing over degrees
Sorry,
of
what?
freedom, you're marginalizing over the unknown degrees of freedom.
It's
There is no kind of
complete.
I mean, this is all.
Yes. This is all very well understood in statistics. What I'm saying is that statistics misses the point of the physical world because the physical world is not random.
I think.
He's arguing with Sean.
Having looked at them a bunch, like if you're writing the simulator, you're just going to call those different seeds in your ensemble method and simulate all of the noise in your trajectory. So I think you can like run multiple seeds for what the wind is.
But ignore wind. Think about humans. You're doing autonomous control of a vehicle,
Right.
and there's this child. Do you know if he's going to run on the road or not?
I don't. That does not make the child random.
Oh, it does.
No.
The child is random.
I think we're going to get stuck.
Okay, this is a deep philosophical discussion which you can continue, but
All you're saying is that there's a difference between uncertainty and Gaussian noise.
Yeah.
Everybody just assumes that all uncertainty is Gaussian noise. That's crazy. You have to be crazy, yeah, right? Yeah. You have to be crazy, and yet.
I'm saying that, but that's not important. What I'm saying is that when you're controlling a physical system, even if you want to replace uncertainty with noise and think of the same thing, both the uncertainty and noise are very small. And they're certainly not jittering the system like crazy, which is what an MDP would do. Which is why, sorry, what?
I'm thinking about, like when you have touching parts and then they may touch or may not touch. If you try to model that exactly like in a real world situation where you don't have exact state knowledge, you're going to run into
So
serious
state
trouble.
uncertainty is a separate issue. It should not be confused with dynamics noise. So you can have noise in your sensors, and that's actually real thermal noise, and it could be quite large. Because of that noise, you don't know what the state is, but you do know that whatever the state is, there's going to be a perfectly nice and smooth deterministic trajectory starting from that state. You just don't know what the state is. You know it's not going. Look, there's a big difference between a trajectory starting at an unknown place and going straight versus a trajectory doing Brownian motion. Like, I hope you can agree with that, right? MDPs model the world as Brownian motion, which is a joke, yes.
Maybe I think that also I agree with, right? But the other thing I think you're trying to say here is that if the uncertainty is large or significant, you're going to be in trouble, right? We don't do control in those cases.
Of course, yeah, you buy more sensors.
Yeah.
Like you don't before you start doing control. Okay, so fine. Okay, so this is the.
In certain cases it happens, in some other cases it doesn't happen.
Self-driving cars don't work, right? We don't have self-driving
But
cars.
planning,
We
planning.
don't have self-driving cars. Airplanes try to put yourself in a state where you don't fly through thunderstorms. Because if you do, you'll crash.
No, like people do this. You know.
Right?
Okay, guys, look, this is a discussion point. Let's move on. So here's.
I have a quick comment on the back. We do control when there's lots of stochasticity, but sometimes we just model it as a banded problem. So if there's lots of stochasticity, we can't project like consumers' behavior, etc. We could just treat it as a one-time step problem.
No, I'm fine with that.
Again, let's say we just don't do control. In those cases, we do control. We just do it.
That's what I'm emphasizing. I'm talking about physical systems. Once you go into like stock markets, social things,
If
humans.
you kick a ball,
Sorry, what?
if I kick a ball, you can really predict where it will land.
After 10 milliseconds after you kick it,
No,
yes.
no, before. Come on.
But that's not the same thing as an MDP. It's not an MDP. The ball isn't like doing that. It's moving on a parabola.
I actually agree with Samo that there is no real noise, but maybe it's useful to be model noise sometimes, even though
Sometimes,
we know that the
yes.
physical systems are not.
Sometimes it's useful. It's just not most of
It's
the
a
time,
tool.
and not when you're controlling a machine.
The reason is because we don't have a good model, that's why.
Okay,
Yeah, it's
look,
ignorant.
let's.
When do you go?
All right. So here's how you can do policy gradients very easily if you do the following. Actually, that covers your ball kicking example. We're going to absorb all noise in the set of initial states. And the set of initial states is going to become part of our problem formulation. So you give me the initial states that you believe are interesting to you, which would be like 10 milliseconds after you hit the ball in 5 different ways. And that from that point on, I'm going to assume everything is deterministic. There's a bunch of trajectories, there's dynamics, there's a policy, there's some parameters, and now the cost is just a function of the trajectories, which depends on the parameters. You can roll it out. This, by the way, resembles the notion of a mini batch in supervised learning. So what do you do? So there is stochastic gradient descent. What is stochastic about gradient descent? Well, the neural network is perfectly deterministic, thankfully. That's why the whole thing works. The only thing stochastic is that you pick a random subset of queries, right? So you can think of that as picking a subset of initial states that you want to care about. After you pick your random subset of images
And there's noise.
in computer, so after you pick some random images in computer vision, then after that you roll the network deterministically, you do backprop deterministically, you do gradient descent deterministically, and encode stochastic afterwards. We can be doing that with policy gradients, and we're going to save ourselves a lot of pain of sampling, worrying about the bias, variance trade-offs, and so forth. And I mean, it's pretty trivial. You can just do the math. Basically, you need a recursive thing over time that propagates the sensitivity of the state with respect to parameters, and then you just do chain rule, basically. There's nothing to it. We've done this about 15 years ago on simple systems. It worked like a charm. We didn't even call it learning because it looked like a solved problem, basically. So we wrote papers about neuroscience, modeling how the brain works at the time. Now, here's the last thing I want to end with. Point about optimization. There's a distinction between optimization and discovery. And that happens a lot in what I do due to contact dynamics. So imagine a landscape that looks like that. It has some kind of nice behavior. If I start too close to that, gradient descent and 20 other things are going to work. But there can be these large landscapes where there's no local information whatsoever to tell you where the solution is. And so if you start somewhere here and going to here, that's what we call discover, like some big change that a human may envision and make it, and then once after that change, good things happen. But there's no reason to expect an optimizer to figure it out automatically. You could sample, but then sampling grows exponentially with the radius of how far the good solutions are, gradients don't work, etc. Why does this happen with contact dynamics? Here's why. Suppose I'm here. My goal is to move that laser pointer. I start moving my hands around. There's no contact between me and that. The cost does not change. In fact, if I move my hands, the cost goes up because I'm expending energy, but the task isn't getting accomplished. So no sensible optimizer should ever discover that, oh, by the way, I should take a few steps and touch that thing and then start manipulating with it. Unless the human designer puts some information under the hood and doesn't tell the reviewers of their paper. Right? That's the only way that can actually happen. Here's an example of that. This is experiment. This is something that we did a couple of years ago. So I'm just show you some results. So these are a bunch of neural networks trained with policy gradients that I'll explain in a moment. They do pretty complicated things, so hand moving objects to targets. So this just shows that it works for different initial and final conditions. Here we tell it the desired position of this obstacle, figures out how to put it there. It works again for various targets and such. So this is a pre-trained neural network, which is running it to show that it does the job. Here the goal is to hammer that nail, and it happily does that. Here the goal is to open a door, and it does that. Now, if you just do RL training with so-called sparse rewards, most of these problems actually have this feature, like your hand has to do something before something else happens, and you basically have to wait forever. Ironically, the only thing that actually works is that pen example. From a control perspective, that may be the hardest task. From an RL perspective, it's the only one feasible because you're in a situation where if you start wiggling your finger, something will happen. And so this is complicated, but you're in the regime. The RLC just doesn't get off the ground. If you start shaping it, you can kind of do it with a lot of labor. What we did is something called demonstration augmented policy gradient, which is basically a very simple idea. You do policy gradient on a composite cost that's the usual cost you would optimize plus an imitation cost. What does that mean? It means that we're going to evaluate our policy on a bunch of demonstration states in some database, and we're going to ask the policy to stay close to whatever that demonstrated it. And that makes a dramatic improvement. So one way to solve this discovery problem is to just download the knowledge from a human brain into a network via demonstrations. So let me just show you. It's a bit of comic relief. This is a little robot that I built. I kind of copied it from Vikash and made it better. I have 4 fingers instead of 3. That's why it's better. So here I'm heroically trying to teleoperate this thing. And it's really hard. Actually, by the way, that may be the only example where anyone has successfully done like teleoperation of dexterous manipulation where you actually make and break contacts. Usually people do grasping and moving, but this thing is ridiculously hard. You need a very specialized system and pretty clever software aids to, like, for example, the mapping here is not one-to-one. I had to invent quite a few things. It's a pain. And if you're trying to like teleoperate something like a humanoid or whatever, it's hard. Discovery is usually done by humans in the real world. We would like to think that the computer just hands over policy to the robot. That's not true. There's actually a human up there. What the human does is informally observes what happens and goes in and makes important structural changes, which are really the reason why anything works. Just look through some examples. So in Boston Dynamics, these are the humans up there, it's ADSI. They have this approach of these multiple regions of attraction with basically a bunch of state-dependent simple controls that they tune by hand. In our case, we had these value functions for MPC that really need to be tuned. If you look at OpenAI case, this is interesting. This is a new toolbox of knobs that the humans can tweak. So you do this domain randomization. Like you randomize various aspects of the model, you throw it in, you retrain. But what do you randomize? There are infinitely many things you can randomize. There are very few you can actually do in practice. And which one once you pick matter a lot. And so what they randomize this, that, and the other, and that's where the human intuition comes in here, what to randomize next. There's no way to invent that automatically, and that's critical. And we've been working on something called contact environment optimization, which is a way to do automated discovery in the specific domain of contact. So when that nasty landscape is caused by contacts, we kind of have an automated way to handle it. In general, you cannot handle it because in general, that would mean doing global search somehow, and that's not tractable. But if you know something about what's causing that nastiness, you may be able to handle it. So here the idea is this. So in these situations where contacts are the only thing that gives you control authority, you need an automated way to discover which contacts are good for you when. And one way to do it is to allow yourself some kind of virtual contact forces that can act from a distance, that can accomplish the task for you if possible. But then you're going to penalize them. And you're going to penalize them in such a way that if I'm here and the thing wants to move forward and I can be like a Jedi and say move and it moves, That's the virtual contact force. Now the solver is going to say, oh, you want to move that thing. Great, but you have to touch it first. So now the solver will give me the power to do that, put that virtual force, but it will also automatically add a cost on that distance. And the optimizer now will know that it has to go and snap into that configuration. There's a formal way to do this. Unfortunately, I'm out of time, so I'm just going to play some videos for you and we're done. So this is the work of Igor Mordak from my lab. Let me just go to the more impressive things. So this whole thing is optimized as one movie, like all these contact points and such. You can tell it to go to various positions. Let's just fast forward through it. You can do handstands. Can walk over obstacles. So in each one of those cases, it's the inverse dynamics trajectory optimization. So the whole trajectory is optimized as one. If you don't do this virtual contact force magic that I told you about, any solver would get stuck because we're in this nasty green shape thing where there's no reason to make progress, actually. But if you allow contacts to kind of give hints to the optimizer automatically, then good things can happen. I'll try to briefly explain how. Maybe I should end. OK, no, I'm told not to explain anything briefly. OK, thank you for listening.
Take one final question before the break.
What was your brief explanation?
Sorry?
What was your brief explanation?
The brief explanation is this. I'm going to have a cost function preprocessor. I'm going to discover terms that are quadratic in the applied forces, including the non-physical forces. And I'm going to allow myself to invent virtual forces that explain away some of that cost. And then I'm going to put a regularizer on it, which has something like a complementarity condition, which says if you invented a virtual force, you'd better close the distance between those two contacts. And now I'm going to replace that quadratic with a cost, which is defined as the minimizer of something. So in order to evaluate that cost, I actually have to solve an optimization problem on an inner loop. Conveniently, it happens to be a convex QP, so it's fast. And then I can evaluate it. I can differentiate it analytically at that solution. And so then my master optimizer is just seeing some weird cost, which happens to evaluate itself by calling another optimizer. But that's OK, because it can do that.
Can we implement this contact invariant optimization for optimizing any trajectory where there is impact from the ground, like with the contact?
You could, but the thing with impact with the ground is gravity is going to make it happen without you trying. So I'm not sure you would gain anything there. Where you gain is like if there's some contact that if you have to take a sequence of actions that's going to establish some contact, which then allows you to do something else, then this thing is very helpful. Something like falling and hitting the ground, gravity does that for you. So I'm not sure. I mean, you can use it, but I'm not sure you're going to buy you anything.
OK.
All right, thank you.
All right, welcome back, everyone. Our next speaker is Emma Brunskill from Stanford. She's helped us understand a lot of these sample complexity results for MDPs and things, and has also has a lot of practical impact herself. So please take it away.
Thanks, I'm so excited to be here. I've had the pleasure of seeing a number of you at different conferences this summer, so I tried to select a subset of things that I thought would have minimum coverage from what everyone's seen. I want to start with a question that came up a few years ago, which seems particularly appropriate being at University of Washington, which is, together with my colleague Zoran Popovic and some of our graduate students, we were interested in the following question. We were really interested in trying to help people learn things better, and Zoran and his team had developed Refraction, which is a game to teach people about plane fractions. And so you can see here that people learn to split laser beams in terms of certain fractions, and they have certain splitters. And the question that we wanted to look at in this case is, how do we keep people playing this game and persisting even though part of it might be difficult? And why might this be a reinforcement learning problem? Well, what we could do in this case is, depending on how the students were doing, or the learners were doing, we could change what they saw next. So as a really simple decision policy, you could think of something like just conditioning on the feature of how long they took to complete the previous level and giving them different next game levels according to that particular feature. But of course, there's a huge number of features that we could be capturing about how students are interacting with the game. And our particular question and opportunity was that we had about 11,000 students' data who had played this game with random levels. Now, overall, I think about 500,000 students have played this game, but we had a subset of it, which we did some random experimentation, because we were curious about what could help students persist for longer and how we could make that personalized and adaptive. And so our goal in this case was to learn a new decision policy to maximize student persistence. And it was then, so this was about 5 years ago, and this was my first start of thinking about how could we use old data to try to optimize future performance. So this is not the exploration problem. This is a case where we have a fixed amount of old data and we want to think about how we use it in the future. But I want to highlight that I think this falls into sort of a general legacy of thinking about reinforcement learning to amplify human potential and to benefit people in general. So while we're very familiar with sort of some of the amazing successes that are happening in the context of games and robotics, there's really been this parallel legacy of thinking about things like adaptive clinical trials, teaching machines. This is one from about the 1960s, and others where we could think about using AI and reinforcement learning to try to do personalized adaptive interfaces that are going to help people accomplish certain tasks. And I care about those applications a lot, and I also care about the technical challenges that they introduce. So if we think about how these are different than a lot of the existing sort of technical challenges that come up right now in some of the amazing successes we've seen, in the context of things like Go and in a lot of robots such as Mujoko, we have a simulator of the domain. And we therefore either have a simulator or we have an enormous amount of data to train in that simulator. And we can always try out a new strategy. And while it can be important to do sample efficient learning in these cases, ultimately, it's okay if we fail to play Go well for literally trillions of games, as long as when we finally have the championship game, we can learn well. Now, in contrast, if we think about sort of interacting with people, we're working on it, but we still don't have a good simulator of human physiology, behavioral learning. And so we can't just run things sort of, with simulated human learners for millions of trials. And at the same time, if we want these systems just to be live, then that has impacts on real people. And so in the context of the educational systems I think about, I don't want to fail to teach 1 million people fractions before we learn a good strategy. So really in my lab, we've been thinking a lot about sort of techniques to minimize and understand what is the data that's needed in order to learn to make good decisions. And I think this is both sort of a foundational challenge in reinforcement learning, but it's also one that if we could figure this out, then we could just learn to make good decisions faster, and then we could benefit more people. So if we treat the number of people in the world as essentially a finite budget, if you need a lot of them to learn a good policy for the rest, then less people are benefiting. So that's why I think this is very an exciting thing to think about. And I'm going to tell you briefly about what I'm not going to tell you about much for the rest of the lecture, which is, of course, a key question in this is how do we do smart data gathering and do efficient exploration? And so a large amount of my lab's work over the last 5 years has also thought about this question, particularly trying to answer this question in the tabular setting. And I think at this point now, we've basically closed that question for episodic tabular MDPs. There's also been some great work by colleagues over at DeepMind, closing this for regret first, and now we've closed it for PAC. But I don't want to talk about that so much today. I want to talk more about this issue I raised earlier with the fractions case. And before I do that, I just want to make sure we're all on the same page in terms of notation. So I'm going to use S to denote state, just like John Tzitsiklis did, for those of you who saw his talk a few months ago. I'm going to use pi for policy. I'm going to use V for the value function indexed by pi if we're looking at a particular policy. And I'm going to think about there being a dynamics and reward. And of course, in general, we don't know the reward function or the dynamics model. And in general, I'm going to be considering stochastic functions as opposed to deterministic. And the question that I'm curious about today to talk about is, imagine we have a data set D of n trajectories. So someone has previously gathered this data with customers or with students or with patients. We may or may not know what pi b is. In the context of healthcare data, we often don't know what pi b is because that's actual physicians making decisions, and they don't normally write down their decision rules for us. But we have this access to this data set, and we want to think about how we can use it in order to make better decisions in the future. So this is a challenging problem for a number of reasons. The first is that it essentially involves counterfactuals, or what-if reasoning. So if we have a sequence of patients that are being treated with sequences of different trajectories of patient treatments or exams, et cetera, and then we have some sort of outcome about health outcomes, then the question we might want to ask is, when a new patient comes by, what should we do? And what's going to optimize their health outcome? And the challenge in this setting is that we have censored data, because we can't actually see what would have happened if I had treated this particular girl with a different sequence of treatments. And of course, this issue arises even in the context of multi-arm bandits, but it becomes particularly challenging in the reinforcement learning case. So we have this censored data problem, and it gets worse and worse with sequential data. But I think the other thing that comes up particularly that's not as present in bandits is this need for generalization. Because if we think about making a sequence of decisions, and let's imagine for now we have a finite set of actions, then the combinatorics of the number of different possible sequences of actions grows up exponentially with the horizon. And yet we're not going to want to try exhaustively all different action sequences. And so we're going to need some way to do generalization. And that's typically going to require us to do some sort of parameterization of our policy or our models or our value functions. Now, I think it's a really exciting time to be thinking about this. There's, of course, been an enormous, wonderful literature about causality and causal inference. And then now there's been starting to be a lot of interest in combining this with machine learning. And to me, one of the reasons this is so exciting is because people in epidemiology and econometrics and biostatistics have been thinking about these issues for a long time, but from a very different perspective. And so I think it's a really exciting time to start combining between these insights so we can sort of unlock all of this observational data that we have access to now. Now, in the substantial literature, a lot of it has focused on the treatment effect estimation problem. The idea of saying we want to make a single decision, a one-time step, and decide between, say, a control and a treatment in particular. And we want to be able to estimate the effect size of doing that treatment compared to the control. But when we get into the reinforcement learning setting, we have this challenge of covariate shift. So in general, of course, different policies are going to take different actions and result in different state distributions. And I really like this, this figure that was in a Nature Medicine paper from some colleagues, David Sontag and Finale Joshi Velez's lab, which illustrates the challenge. Some of you might already be familiar with this, but I think it's a nice thing to go through. So let's imagine that we have a whole set of patients, and then we want to evaluate a particular decision policy. So we first say, well, our decision policy is going to do mechanical ventilation on these patients. And so then suddenly a whole bunch of the data that we have is excluded because those patients didn't get mechanical ventilation. We then say, well, what if those patients experience discomfort? Under our policy, we would apply sedation. And then again, a whole bunch of people did not get sedation, so we can't use their data. And you can repeat this over time steps. And so you can see that if you look at sort of a really large, maybe 100,000 patients, which is a reasonable number of patients, if you start to winnow out the number of them that happen to get the decision policy that you care about evaluating, then you can start to really shrink the cohort of people or the amount of data you have that matches. And so that becomes a really big challenge because as we have less data, we expect to either start to need biased estimators or high variance estimators to try to use this data to figure out what we should do for new patients.
Why do you think it's representative? It's even more worrisome.
What do I think? What?
The end thing that you got is a representative sample of what would have happened if you run your policy.
It's a great question. So why do I think this, even for these, 6 people that I have left, are they representative? It's a great question. We'll have to make some assumptions under whether or not we have certain features that can cover how we're going to generalize in terms of what features are describing the patient. And then another really important assumption we're going to have to make is that the variables that were used to make these decisions are available to our algorithm. So essentially that there's no confounding. That there aren't decisions being made. So for example, maybe somebody has one blue eye and one red eye, and that's totally critical to use to decide what your patient treatment is. If I don't have that in my notes, if my algorithm doesn't get access to that, that can lead to estimators that are wrong, essentially, because we're not having access to variables that we need to have in order to make good decisions.
So are they let's say take mechanical ventilation.
Yes.
So part of the people that didn't get it,
yes,
your algorithm will say that you should give it to.
Maybe, depending on the value.
Right, depending on the value.
Yes.
But those, so this is what I'm really worried about.
You're worried about for these people that didn't get it?
Selection bias, right?
Exactly. So that's my point. So well, there's 2 things. We're going to be in the potential outcomes framework for those of you that are familiar with that, and that's going to make, and we're going to have to make sequential potential outcomes framework assumptions, and we're going to assume that there's no confounding, so that we would have had all the variables we need to make that decision, and so then we are going to be able to extrapolate to what would have happened to those people who didn't get it if they were to, assuming we have access to all the variables. Yeah.
Just a clarification question for that. So you mean that at the time when the mechanical ventilation decision was made, it was made by some doctor, and the doctor was looking at some characteristics of the patient, and you have information that they were looking at exactly that same information, and your policy can be based on that, and that will be the assumption.
Yes, so we have access to all the covariates that were used by the doctor to make the decision. And while in some ways that seems like an incredibly strong assumption, at least in the US, we have a fairly strong legal culture around medicine, for better or worse. And what that means is that people have to do a lot of documentation. So I think that a lot of our electronic medical record systems right now don't have that information in easy form. But as we get better and better NLP on those notes, I think it's not a crazy assumption compared to what I would have originally thought, which is this is always going to be impossible. I'll go back to this more later. I will say that one of the big things we're doing in my lab right now is to try to understand if there is confounding, what can we say? And can we get bounds on the resulting values even if confounding is possible?
Specifically, when you say confounding, what do you mean? Do you mean a missing variable?
You know, a missing variable that is used to make a treatment decision that we don't have access to. There's a lovely example of this. Some of you might have heard of it. Some people used to conjecture that smoking was not related to lung cancer, and there was another missing variable that caused you both to be more likely to smoke and have lung cancer. And they did this sort of a confounding analysis to show that in that case, the amount of sort of confounding that was going on would be enormous. So sometimes you can say, if you have a limited amount of confounding, it can't affect your estimate of the treatment effect that much. So this is why this is challenging. Oh, yeah.
Quick clarification. So are you starting with a set of homogeneous
Sorry, what?
patients? Are you starting with a set of homogeneous patients?
Good question. No, we don't have to be. So this is, we don't have to assume that we have a complete coverage over the state space, but that's going to restrict, we're not going to be able to make assumptions for initial states we don't have.
So in this case. When you started like deciding who would take the mechanical ventilation, is that like you're thinking, because their patient's characteristics are not the same, so how?
Right. So we would have access to all those variables, and in fact, some of you might have seen the recent DeepMind paper that was talking about. I forget actually what the medical condition was, but it was mostly over males, and so they can make assumptions that are saying like, for males, this is how well this policy would do, or this, these are how well our predictions would do for males, but they can't generalize to females well because they don't have very much data, and they can talk about how well they do in that case.
Deep learning was just going to generalize and solve it.
That is the goal. Not sure everyone here believes that. So, okay. So this is the general thing that I would like to be able to solve. I would like to say we want to pick the policy, or we want to do counterfactual policy optimization, which is I want to take my data and I want to figure out what we should do in the future. And let's say we want to do something like the following, which is we have a set of hypothesis classes, and I'll talk in a second about what those might be. We want to figure out the best policy in the best hypothesis class that has the best performance in the future. So here I'm looking at an estimate of the value of that policy in the future. And you might think this is a reasonable thing to do. We're sort of just getting a good estimate, and then we're taking the best of those, whichever policy has the best estimated performance in the future. Unfortunately, that's not sufficient. So my student Shayan Daroudi and I and my former postdoc Phil Thomas showed a few years ago that you can't just do this. And as often I find in science, the answer is obvious in retrospect. So why is this true? Well, this is just an estimator of the value, and different estimators will have different amounts of bias and variance trade-off. In this case, we were looking all at unbiased estimators, but some of them have very high variance, some of them have very low variance, and if you're taking a max over estimators with different amounts of variance, you might make systematically bad decisions. So we can't just look at sort of what our estimator says. We're going to need some notion of the quality of those estimates. And so that's what's really led me into, at my lab, kind of into this journey of a quest for sort of, batch policy optimization with generalization bounds. And when I talk to my colleagues who are in supervised learning, they always look at me sort of quizzically, because they're like, we have that, it's called structural risk minimization. Or they say, we have empirical tools for that, it's called cross-validation. And I said, yes, I know about both of those things, but in RL it's harder for a number of reasons. And I just don't think we have these yet. I think we're making steps. And I think if we could do it, there'd be so many application areas that we could do a much better job at. So what would I like us to do? I'd like us to say, I want to figure out a policy that basically has the best bound on how well it's going to do in the future when I deploy it. So I don't really care about how well my policy does on my training set or my existing data set. I want to know if I deploy it in the future on average, how well is it going to do for students or patients or customers? Yeah.
Just wondering about whether, you really insist on that you should have a sequence of hypothesis basis, or should you just have a bound that the deviation bound and the interval lengths will depend on the policy and how it interacts with the data, right? It seems that you have this additional structure.
You mean here,
yeah.
in this case?
Yeah.
I'm putting this in here so we can also take into account model selection. So that we can think of you to also saying, do I want to use a linear policy class versus a deep neural network policy class, and which of them, so I can trade off between those.
Those are, artificial boundaries that you may not need actually, because you should be comparing policies to policies, and how certain you are about your estimate of the value of the policies.
The reason why I would like to think about it in that case, I think it's a good start. The reason why I've started thinking about it more in this case is that I think the bounds that we have right now tend to ignore any structure in the policy class or value function that we have. And in structural risk minimization, we take advantage of that to get us generalization bounds. And I would like to do the same. I'd like to say, I don't want to make assumptions about whether my world really is linear. I just want to say if I make an assumption that it's linear, this is how well you're going to do in the future. And right now, we have to make assumptions like the world really is linear, and I don't want to do that. So we can think of this as involving three different things: policy optimization, policy evaluation, and error bounds. And I think the part, I guess I'll first just say, I think it's already different than structural risk minimization because it's not clear even which sort of hypothesis classes we're talking about. So when we think about hypothesis classes, we could think about there being models, like dynamics and reward models is what I mean by that, or value function approximations, like deep neural networks or linear value functions, or policy classes. And so it's already, we have a lot of different choices of even how to represent decision problems compared to a lot of supervised learning problems. So we've done a lot of work on policy evaluation. What I want to talk about today is policy optimization. And I think the real challenge here is having good error bound analysis so that we can do policy optimization, you can do policy gradient, we can do lots of different things. The question is, how is it going to converge? Are we going to do well? Do we have any sense of how well it's going to generalize in our future data? And I'm going to argue that I think the existing error bounds have a lot of limitations, including work that we've done. So important sampling bounds are possible for these cases, but they tend to completely ignore the hypothesis class structure. And so generally they're very loose. It just means we need a lot of data. And so in some cases that's very reasonable, like Phil Thomas had done work with Adobe. If you have millions of records, I think this is totally reasonable. When I look at some of the mobile health applications we're curious about right now, I think we're gonna have on the order of hundreds or thousands. So I don't think these are gonna scale. Things like if we make certain assumptions of our hypothesis classes, like kernel functions or averagers, we can get this type of bound, but we typically need a number of samples that's exponential in the input state dimension. If we want to be able to capture all the covariates that describe patients or customers or students, I think that's not going to be feasible. And I think there's been, fitted Q iteration is really interesting to me for a number of reasons. One is that it's been around for a long time for batch reinforcement learning, but also it's sort of in some ways the foundation of deep Q learning. And so if we could better understand that, it's going to give us insights into deep reinforcement learning. The challenge I see is that a lot of these bounds require pretty strong assumptions about realizability or bounds on the inherent Bellman error. And in particular, the bounds that I'm aware with, and maybe somebody will know of additional ones to point me to, mean that if we're not realizable, we're going to have bounds that depend on unknowable quantities, like the inherent Bellman error of a function approximator in a particular domain. And the problem with that is that's going to prevent us from doing model selection. Because if we have a linear class versus a deep neural network and we can't evaluate those bounds, I'm not so concerned necessarily about exactly what those values are, but I want to be able to compare them. And so I think that's one challenge with these type of analyses so far. And then there's also been some really interesting new primal dual approaches that are really promising, but they typically have similar dependencies. So I think this is really hard. I think it's a really exciting direction. I think there's a lot to be done. I'm going to move the goalpost. Oh yeah, Alec.
So we have structural risk minimization in theory with using the uniform convergence bounds, however refined we want to make them. But I feel like in reality it only works because we can do it with cross validation, right? And that's going to be a much better behaved estimate. Do you really think if we didn't have cross validation, structural risk minimization was going to work in supervised learning?
I think it's a great question. I think it might have still been useful for model selection. So I'm not sure it's going to tell us whether this is good enough for us to deploy or not, because the bounds would be so loose. But I think it might allow us to still say, do you want to use linear or do you want to use quadratic? Maybe. It's tricky about how loose those are. But I also would absolutely argue that we want cross-validation for this scenario too. Yeah?
Isn't there a problem or two problems with cross-validation in this domain? So one of the problems is that you still have the old policy issue. You still have to have the variance issue that you have to control. If you need to do a selection at the end of cross-validation, you need to know the deviation bounds for cross-validation.
Well, I'm not saying that cross-validation is going to work here. I'm saying that
yes.
This is not necessarily a viable alternative in my mind.
Well, it seems to me that cross-validation is calling for the same type of analysis if you take it seriously, and if you're worried about that you might be overfitting to the noise. And in these settings, you're very prone to overfitting to noise. In cross-validation, you also need to make sure that your algorithms are stable. If they're not stable, and no one knows, for example, if you use neural networks, whether they're going to be stable the way people use them, right? It's kind of like, yeah, it's in practice, people will continue to use it, but it's actually working or not, that's a good question.
No, I guess I'm saying that I'm using these as high-level inspirations. I don't think we're where we want to be for either of those. I guess I'm using cross-validation as a loose way to denote we would like an empirical way to do this. I don't think this is an empirical way, to Alec's point. And I think we'd also like theory. And I don't think we've got either at this point. OK, so this is hard. Let's see if we can do something easier. At least see if we can do the easier thing, and then we can hopefully go back to the harder thing. So an easier thing to do is to find a good in-class policy, given the past data, and not necessarily have any bounds on future performance. Just say we're going to try to find something that seems to be good within a parameterized policy class. And while that seems like I've just made it much, much, much easier, which I sort of have, I think that it's not totally unreasonable. And I'm going to argue later that for interpretability reasons, this might be a nice place to put in some human knowledge. So I think there's good reasons to think, at least in some of the applications I consider, that having policy parameterizations might be a useful place to put in interpretability knowledge and get benefits. Okay, so can we do this? So to be specific clear, what I want to do right now is I'm going to do some form of policy search or policy gradient, but I want to do it only with batch data. So a lot of the methods right now that are considered off policy gradient still actually are gathering new data in the environment. I'm going to be restricted to saying I've only got the medical records that I have or the data that I have. Okay? So one of the reasons we are curious about this is that I think policy gradient methods are enormous, as you were just hearing from Emo, and I think many others are familiar with it. If we look at, but there hasn't been that much work on the batch data setting. And I also think that one of the other reasons why I care about this is that I always find it kind of frustrating that in the vanilla policy gradient algorithms, we just talk about throwing away all the old data from the previous iteration, which seems insanely wasteful. And in sample, in cases where those samples are people or other high stakes scenarios, it seems like surely we can do better. Now, people have certainly tried. The problem is that if your policies are quite different over time, the variance you introduce can be too large, and so you might not get a benefit. So if we look at the policy gradient theorem, we can think of it as the following, where we have sort of, we think of the value of a policy as being the sort of integral over the value of each state times the stationary distribution over states under that policy. Now, if we think about sort of expanding these out and thinking about what we get in these different scenarios, then sorry, I have more animations here than I expected. Then if we want to use this for a different policy, then we're going to have some challenges. If our data was gathered, let's say, under a behavior policy mu, and now we want to evaluate the value under a different policy, the problem is that sort of our distribution, that d pi, our stationary distribution over states, is going to change because our policy is different. And so one of the previous algorithms for trying to look at this said we're not going to deal with that aspect of sort of the covariate shift. Our covariate shift is both going to change the actions we take and the states we reach. So in this nice paper by Degree and all, they looked at sort of, well, what if we keep looking at just sort of the stationary distribution under our original behavior policy, the policy we use to gather our data, but we're going to account for sort of the difference in the actions we take on top of that. And this had some nice empirical performance. You can now use it offline. The problem is that you're going to get a bias of your gradient estimates. Because you're not really, this isn't really the value function you're going to get when you deploy, because you're generally going to reach different states. And in fact, if you don't reach any different states or take any different actions, it's going to be exactly the same. So what we would like to do in this case is to think about, well, what would we do if we wanted to actually correct for this? Well, we could think about sort of using an importance sampling technique to reweight our data so it looks like it's from the distribution of the new policy that we want to evaluate. The problem is that if we do this in sort of a naive way, and I'll expand this in a second, we're going to get a really high variance estimator. And I think to see this, it's useful to think back about sort of the standard importance sampling for reinforcement learning. So in importance sampling in general, if we think of the value as being sort of what's an average over the probability of a trajectory, so I'm denoting that with tau, times the reward of a trajectory. So the beautiful thing about importance sampling is that if we have data from a different distribution, from a different policy pi b, then we can just reweigh it, so we can leverage our data from our behavior policy pi b, and then we have this ratio. And because the dynamics is the same in both environments, then we just get this ratio that depends on the actions. I know everybody here knows that, but I just want to contrast that in a second. So that's been the first time I'm aware of people doing that for RL, is sort of doing a pre-cups paper from 2000, but there's been lots of extensions and continues to be, including from my group and others, to think about the variance in these estimates and things like that. I think one really nice direction that's happened in the, yeah, sorry.
Okay. Emma, what are you imagining about the batch data you have in the past? Like, are there states that is it that every state you've seen in the past has every action played in the past?
Yeah. So we're going to have to make an assumption to get, we're going to make an assumption. So Daniel's question is, what assumption am I making about the coverage of the behavior policy? And I'm going to make an assumption that the behavior policy is going to cover one of the optimal policies. So it doesn't have to be all of them, but it has to cover one of the optimal policies that I'm going to construct. Well, I'll say in a second, and then you can tell me if it answered your question. So in this case, we see this ratio. Oh yeah, sure.
It's also related to Dan's question. So when you have these behavioral policies, you have the data that's collected, but when you're doing blend sampling, you need to know the ratio. So are you thinking about some propensity score here, or how do you get?
Yes, great question. So you mean how do I get these?
Yeah.
Yeah. So in some of the work, we assume it's given, like that we have an algorithm, and like in our fractions example, we knew what it was. In that case, it was random. In other cases, we're going to estimate it from data, and under certain assumptions of asymptotic consistency, it'll be fine.
So like in these healthcare settings, you're estimating it.
We're estimating
These numbers are
from data. So we have a set of covariates, and we estimate the probability of the action from those. And we're going to need assumptions of coverage, almost always, that the policy that we're, well, we can either assume that this is going to cover everything that we want to evaluate, or if you're making assumptions that your rewards are all 0 or above, then this may just give you a lower bound on the value function if you don't have coverage. And so that can still be okay for optimization. So the nice thing so this is generally bad because this is going to depend on the horizon, and we, and I'm sure other people too, have proved that this variance of this estimator can generally be exponential in the horizon, and so that's horrible, which is why I think nobody uses this in practice for long sequential problems. But one really nice insight that was made, as far as I can tell, kind of in tandem with 3 groups over the last couple of years, is just to say, well, this particular way of writing down the value function in terms of a probability of a whole trajectory times the reward of the trajectory is not the only way to do it. And the other way is this way that looks very similar to sort of the policy gradient theorem I was saying before, which is what is the stationary distribution over states and actions under this policy times the reward of that state and action. And just to be careful here, d pi here is now going to incorporate the discount factor. So it incorporates sort of the weighted sum of discount that you're going to be in the state and action. And the nice thing is that when we write this down here, then we can play the same importance sampling trick, which says instead of having to think about this product, we just think about what is the ratio of how much time we'd spend in that state and action under the new policy divided by the old policy. And now we've got rid of this sort of horizon issue. So that, I think, is really elegant, and people showed that you could use this and get much better empirical estimates for policy estimation. And so a really natural, yeah?
How is this a function of S0?
How is this a function of S0? Because d pi of SA is assuming you're starting in S0, and it's going to have a discount factor.
And what is cap J?
And what is what?
1 over J at the last equation.
Here's our number of data points. Yeah, so we're going to do an empirical average, like from our existing data set. So this was all for the policy evaluation case. Generally, there were some experiments here that were not, but generally this was all for the policy evaluation case. So our insight was quite a reasonable one. This is also with Alec and led by Yalu, and also with ADSI, that we could use this for policy gradient. So now we're going to take our policy gradient theorem, and we're going to use this ratio of stationary importance sampling in order to get a true unbiased estimator of the gradient. And so now we're correcting for the state action distribution. And we're going to use the approaches that I mentioned on the previous page to try to estimate this from data. Yeah?
So if those estimates are biased, is this going to be bad for us because the gradient is going to be biased as fast? So how are we going to deal with that?
Yes, so our bounds are going to end up, the question Chubba said was, well, what if those gradient estimates are bad or biased? Isn't that going to be a problem? Yes, we're going to be able to have a theorem that depends on these being close but not perfect.
Also, how do you get the, I mean, this looks like a little bit of an odd way to write it, because with the q pi, you'd also have to do the same trick.
We do. Yeah, so we end up having with, Sean's question is like, well, what about q pi in this case? We're going to do an actor-critic style algorithm, and we're going to both use, we're going to use the batch data for both parts. So we're going to have the batch data to estimate the q pi right now and do off-policy evaluation for q pi, and then we're also going to use the data to get a ratio of the current policy. And so it's going to look very much like a policy gradient algorithm, but we're always using the same data. And so we're going to have a current target policy. We're going to estimate this, take a step, and repeat. And in particular, this is the algorithm. So we're going to start off with the behavior policy, just warm start. And then from 0 to t, this is all, again, just computation. This is no new data. We're going to sample some of our old data to estimate W. W is our ratio of the stationary importance sampling. And then we update our critic, and we take a step. And one of the things I want to mention there is, so we have some assumptions under which this, to show that this might be a sound thing to do. So we need to have some assumptions that we saw before over whether or not the policy, the stationary policy over actions and states, if that's 0, that we also in our target policy are 0. So this is basically a coverage assumption. And one of the things we do is we construct this sort of augmented MDP, where we think about if you were going to go outside, so your data is going to cover sort of a set of states and actions. And what we're going to say is that if you go outside of that set of state and actions with your policy, we're going to find the reward there to be 0. And so that's basically just going to give us a lower bound over any policy that exits kind of your envelope of state and actions that we visit under mu. And that's going to be OK in the sense that if we make okay, so what we're gonna make an assumption here is that there's gonna be at least one policy that's optimal that is covered, and then that means that that policy is not gonna go out or is gonna have a value that's at least as good as is in the original MDP. So our pi star is still gonna be optimal, but everything else is gonna either have the same value as it would before or a lower bound. And so this led us to my knowledge, the first proof of convergence to a local optima for a batch policy gradient. We need a few other additional assumptions. Most of these are pretty common. And I think one of the interesting things about this is that we don't have to have all of the policy. We don't have to be able to cover all the policies you're going to go along your gradient updates, only the optimal. So a lot of like FQI style bounds require you to, all of the policies that you evaluate have to be within your space, and you have to be able to evaluate them accurately. We're not going to have that here. Okay. So this is only to a local optimum. Yeah.
So even if the optimal policy is not covered, you could still like improve over the previous policy, right? Like it's
probably. So the question is, if an optimal policy is not in there, can you still improve? Probably, but we're not making guarantees in that case. It would depend whether if one of the policies that is covered is better. So one of the nice things about this is I think it's always nice if there's theory as well as useful benefits empirically. And so we did some empirical experiments to see, well, how much lift does this really give you? And so in the context of something like carpool, this is the behavior policy. So this is like how well your behavioral policy would do in the environment. And if we look at something like off-pack, which is the one that does not correct for the state distribution, but just the actions, it can do a lot better. It can learn, so this learns a policy that's much better than the original behavior policy. But you can see that our approach does substantially better, and in fact basically learns the optimal policy for this domain. And so the nice thing about this is just really saying we're going to be able to do just much better with the same data. It's exactly the same data. We're just doing a smarter policy gradient algorithm, and by correcting for the state distribution, then we're going to end up with a much better policy. It was a little hard to compare to other algorithms because most of them are not looking at the batch setting, but we looked at a couple other ones that are sort of state of the art and adapted them to this case, and these ones don't tend to be able to do as well in this scenario. Sean?
What was the policy? Sorry, what was the behavioral policy?
This was the behavior policy, and in this case, I'd have to look back. I suspect it's a combination of optimal and random.
Uniform.
This is uniform.
So how would the uniform
random
ever get to the
So
standard?
Yeah, this is pretty easy. Yeah, this is a.
Okay.
Yeah, so this is not like a sparse reward problem, or it's not. It is sparse, but it's pretty easy to get under the uniform policy.
Okay.
Yeah. This is not. Yeah.
Sorry, how much data?
Good question. I think in this case, do you remember? I don't. I'd have to go back to the paper. I don't think it's enormous. I don't know, 1,000 trajectories, 10,000 trajectories. It wasn't millions. Like it was. Yeah.
Certainly no more than 10,000.
I don't think more than 10K, but I'm happy to look it up. So the second case that I think is interesting, and this maybe goes to Shyam's point, is so this is a case where under your behavior policy might not be very good, but it would actually encounter good rewards quite a lot still. We looked at an HIV treatment simulator. where that is not the case, where it's much more like a chain domain where you have to take the right series. So something more exploratory or more random is going to do very badly. In this case, you can see the behavior policy is here. And in this scenario, we can, again, we're not going to get to optimal, but we're going to get to much better. And so this goes to the question of before. So in this case, I don't think that the optimal policy is covered, but we can get a substantially better policy than what we see before. And again, this is just with the same data. And so I think that the interesting thing about this is certainly something you can imagine embedding within like an online algorithm too. And this hopefully should just allow us to have bigger steps, right? We can just do more with the same amount of data we have, and so we shouldn't have to collect as much data because each time we can do bigger jumps. So just to summarize that part, and I'll jump to here, this is the first convergence result as far as I know to non-tabular off-policy policy gradient, and in simulation it seems to work pretty well. And so that gives us this, where we can guarantee we get to sort of a local optima. But this is pretty far from the original goal that I was saying that I wanted to get to. And so let's see if we can do a little bit better. So another is that, OK, let's still stay in the in-class policy, but let's not just guarantee we get to some local optima. Let's try to guarantee that we get to the best thing in class. So an oracle might say, this is the best policy in your policy class. And I want to compare to what is the policy that I select. And I'd like to be able to have some sort of bounds which scale with the complexity of my policy class and the amount of data I have. And so asymptotically, I want to be able to get to the best policy of my policy class at sort of, a square 1 over square root n rate. And to my knowledge, we're the first group to do this. This is led by Xinquan Ni and also with a great collaborator, Stefan Wager. And this has been really fun for me because they're sort of statisticians and econometrics people, and it's been great to learn about some of those techniques. We can't do this for all types of policy class, but we can do this for what we call when to treat policies. And so this is something like the following, which is, what would be a personalized policy for when to take the ventilator off? Or it doesn't just have to be a single decision when you stop. It can be you decide to start HIV treatment, and which HIV treatment do you start? So you decide you have an ongoing process, and at some point you make a decision, and it can be one of a set of A decisions. And we want to be able to account for lots of different things in this case, including that we're not going to assume that we know what the behavior policy is, so we can leverage that. We're very interested in this for healthcare data. And you can think of, as an example of this, could be linear threshold policies, but that's not the only ones we can handle. So something like as your CD4 count goes down, then if it drops below this, and you're in a certain range of how long you've had this, then you start HIV treatment. That would be one example of the linear threshold policy. Or another case where, as a function of time step and a health metric, you switch from treatment on to treatment off. And this is where I think the structure we can put in the policies can be very helpful, because these are things that I could imagine visualizing with doctors and saying, like, look, this is what our policy is doing. Do you think that's reasonable? Do you not think that's reasonable? And it can be a nice place to make things a little bit more interpretable. So I know I don't have a lot of time, so I'll sort of flash some of this stuff up. One of the things we were interested in doing in this case is try to have things where we could do, we were really focused on policy optimization, not just policy evaluation. And we wanted to do so in a way where we could be robust to some aspects of how well we can model the probability that people took certain actions, because we're just estimating that from data, and how well, if we're building sort of Q values, how good those are. So let me just step through that and just so I can show kind of the idea. So the idea in this case, and it builds off of Sham's work and Susan Murphy's work, is to think about an advantage decomposition. So we could think about in this case, because I have particular structured policies, of what is the value of stopping now and treating in a particular way versus what is the benefit if I wait one more time step and then treat in that same way. So what is sort of that relative advantage? And if we think about that, we can write down sort of the difference between our particular value of our policy versus a policy that never treats as a series of these advantage functions. And this is a decomposition that both Susan Murphy and Sham Kakade have proposed before, and we're going to use it in the off-policy setting. Yes, I'll wrap it in like zero. And so the reason this is interesting is that this thing on the second-hand side is going to sort of be something we can think of as even like a single time step case. And that's going to allow us to leverage, let me just quickly put this up because The reason I think this is interesting is this is really leveraging some econometric techniques and semi-parametrics, which is something that are new to me but is exciting to learn about. I think that the reason that these are intriguing is because we're going to treat a whole bunch of variables as nuisance parameters. So like we don't really care about what is the probability that the physician decided to treat or not. We just want to use that information to help us understand whether this policy is better. And similarly, like we don't really care about what those mu's are. We just care about whether or not this policy is better. And so we can treat these nuisance parameters and learn them less well than our main target and still have these sort of 1 over square root n rates. And again, just to sort of highlight where I see different communities coming in, Dylan Foster from MIT just got Best Paper at Colt this year for looking at similar stuff for sort of this orthogonality or nuisance parameters in the context of machine learning. So I see sort of there's a lot of interest in bringing this over to control decisions that we might be thinking about in the sequential setting. And so this result, sort of this decomposition, allows us to get these sort of regret rates. I'll just say briefly so I can wind up. We compare to things like fitted queue iteration. As you might expect, if you have very small amounts of data, this is the amount of data we have, fitted queue iteration is generally going to do pretty well because you have a parametric bias. But as you get more and more data, it's it can be stuck. It's not necessarily asymptotically consistent. Whereas if you look at different domains that we have, green is us, as you get more and more data, you're going to be asymptotically consistent and we'll have better regret rates. And I think in terms of the policies that we get, if you look at sort of fitted queue iteration, it doesn't have this structured policy class. So you can kind of have this weird behavior where the policy it learns, it's sort of like, well, wait, if I'm slightly above, minus 2.3, but a little bit less than 0, I suddenly switch whether I turn on my policy or not, and then I go back. Like if I was a doctor, I'd look at that and be like, well, that's sort of weird. Like, is that just a bug? Is that sensitivity? Like, why is that a reasonable policy? Whereas the one on the left, because we've imposed that structure, kind of has this clean, this is where we'd make the decision, is that boundary in the right place? So just to wrap up, I think that there's a huge amount to be done in this quest. I think if we could solve it, we would sort of be able to unlock a huge amount of the observational health records that we have out there. It's not, of course, just my group. There's been a lot of other really amazing work. And I think one thing I just want to highlight there is that I sort of thought this problem was a big thing for maybe education and healthcare, but maybe not so much in sort of, like e-commerce. But I was talking to some colleagues who said, oh no, like actually, even for things like, Amazon and Netflix, if you deploy an intervention, it might be that someone's, maybe Chrome browser's spam filter systematically reroutes this, So often you're going to have confounding or challenges or that mean that a lot of these questions are going to come up in many different types of domains, even beyond the ones that I thought about initially. So just to close, it's clearly a really hard problem. I just want to highlight that I think that there's room for optimism. So if we go back to this example I said at the beginning, we were trying to learn a policy that increases student persistence. In this case, we had the advantage that for better or worse, students drop out fairly quickly. So our horizon is fairly short. And so in this case, we could use important sampling techniques to get a good estimate and predict that when we were going to deploy it, we would increase student persistence by 30%. And so when we did a new experiment, we found that indeed, we learned a policy that increased student persistence by 30%. So I think that's a good highlight for why it is the fact that both these methods really can get estimators that allow us to predict future performance in a reliable way, and that in many cases, there's a huge amount of room for optimization beyond what we can do right now. Thanks.
So you started by saying that generalization is complicated and you don't know anything. At the end of your talk, did you come up with something that looks like automated generalization method, would you say, or generalization is still?
Yeah, I don't know if I said we can never generalize, but I did say it was hard. I think in this case, for like the when to treat policies, we can do generalization. We have something that's a function of how complicated your policy class is. Like this is kind of what our result looks like. It's something that says, if you have a policy class and this is how complicated it is, like as a function of k pi, this is what your regret will be like. So I think we sort of have the structural risk minimization for this type of problem. A lot of problems are not when to treat policies, and so we'd like to be able to extend this to the more general case. But I think at least this is a start towards those type of guarantees.
in infectious disease or infectious disease?
In infectious disease, great question. I have not. There might be in epidemiology. One of the challenges I think about working across discipline is we all use totally different notation, and they tend to call things dynamic treatment regimes. My impression is that I haven't seen a lot of this in infectious diseases, but there certainly might be for modeling. My guess there's a lot of additional complications. So another thing that I'm assuming in this case is that you have independence of treatment. So like if I treat one person, that's not going to have spillover effects. But in like whether it's Uber or infectious diseases, like those you'll have crosstalk. And so I think that's another case where.
That's an important assumption here.
Yes, so there's the confounding issue that we talked about, but then there's also this independence of treatment. And I think in a lot of network problems, you can't assume that. So it's another really interesting direction.
All right, thank you. See everyone back at 1:30.